student here at BU. He is a student of Run's. He has worked on a number of questions relating in quantum computing, and especially in the use of quantum information in cryptographic protocols and how those things connect, both to what extent you can do classical crypto with quantum in sort of a quantum world, and also how you use quantum computing to achieve cryptographic goals. And so we'll be hearing about work along those lines. Take it away.
Okay, thank you. Okay, is the mic? Yeah, I think the mic is working. Okay, so thank you, Adam, for the introduction. So I will be talking about quantum cryptography in Algorithmica. And this is joint work with William Kretschmer, Makran Sinha, and Avishai Tal. And this talk will be featuring the one and only Iron Man, or Ron Kennedy. I don't know who made this beautiful art. So the point here is that Ron actually has monitored me throughout the project and gave me a lot of useful feedback. So in this talk, while I am describing these results, I'll also talk about Ron's viewpoint and his criticism of this work. Since this is a special occasion, especially for Ron. Okay, without further ado, actually, with further ado, let me give you some disclaimers. Some of these slides are freshly baked, meaning, which is a better way of saying I prepared them last minute. So they are not Kennedy approved. For example, this slide, and also the next slide. In particular, every quote of Ron in these slides are fake, but are based on real private communications. Okay, so now, without further ado, for real this time, okay, here's a meme. Ron is saying, I dispense wisdom, and here's me. What is your wisdom? Okay, and Ron begins, okay, computational hardness is not the same thing as computational assumptions, right? People say cryptography requires computational assumptions, but they really mean that it requires computational hardness, not assumptions. Okay, and also random oracles are structured, but anyway. That's a good wisdom. So in the rest of the talk, I will be. In the rest of the talk, I will be focusing on the first part of the wisdom. Okay, so let's dive in. Indeed, cryptography needs computational hardness, but does it really need computational assumptions? That's the question that I am asking for this talk. So to answer this question, I need to first make this question more specific or more concrete. So here's one way of putting it. Which useful cryptographic task X, or by which I mean like practically relevant and or efficient tasks that people are using in practice, so which of those requires you to make computational assumptions under a realistic model of the real physical world up until 1989. Okay, so now that I have added all of those quantifiers, I can almost answer the question. So if I consider most of X, so like encryption signatures, what else people use? Yeah, something like that. And if I want it to be secure against polynomially bounded adversaries, then the answer is I'll need one-way functions. This has been shown in a long line of work from the last century, and therefore, if we have one-way function, then we will naturally separate P from NP. As you might have heard, this is a very hard open question that is worth at least $1 million, if not more. Okay, so this is a barrier. We cannot prove that they exist without just separating P from NP. So in the crypto literature, we make computational assumptions just to get around this barrier. Okay, and you might have noticed that in this question that I posed, there is a subtle quantifier that I added, and that's this part. There's this year of 1989. So what happened in 1989? So this happened. So some people, Bennett and Broussard, they started doing experiments on quantum cryptography, and they started to see that there are like what is known today as QKD, or quantum key distribution, seems to be working in the real world, not just in theory or on papers. Okay, and obviously today we live in 2023. It has been 30 or so years since 1989. So naturally, there has been a lot of development since then. So right now you can find a QKD experiment in an average, maybe I shouldn't say average, but in basically any college physics lab. And there have been a lot of experiments all over the world. China is doing it in space. And you can also purchase one of the QKD kits online. By the way, this might be, I don't have a lot of slides, so feel free to interrupt me with questions. Okay.
Since you asked, don't you need like optical fiber cables or whatever to do this? I mean, there's no point doing this between you and me in the room, right? Because I'll write a key and I'll give it to you. So don't you need like infrastructure to set this up?
I mean, we can't just do it over vacuum or air. Like I can just shoot you laser from here to you.
From this building, we should be able to set up a network with all the other computer science departments in the area.
From this building? You really had to rub that in.
Just saying, we've got
That's supposed to be 89.
Yeah. But the point is, since 1989, we should no longer confine ourselves to thinking about classical, certainly not classical communication, because QKD is not something you can capture with a classical communication model. Okay, so let me revise the question. So the same question: which useful cryptographic tasks require computational assumptions under a realistic model about our physical world, but after 1989, so the year that we live in particular in 2023. Okay, the first thing you'll ask is, can we do some more things like QKD? Can we just get information theoretic security for other tasks? And unfortunately,
So again, back to my point, all you need is the ability to send photons, right, polarized photons, and the chance that a good fraction of them reaches the other end, right? That's all you need. That's what it's back.
yeah.
You also have to be able to generate single photons, which is like non-trivial. That's experimentally.
That's not a communication. Right. Sure. But I was hoping that's what these magic machines.
Right, but it's not supposed to be physically impossible. Okay, yeah, so getting back to the slide, the point here is that unfortunately, even with quantum communication or even quantum computers, you still cannot achieve information theoretic security for a lot of the practically relevant cryptographic tasks like commitments, OOT, availability transfer, encryptions, authentications, all of those things that people care about in practice. Okay, so it appears that QKD is actually the exception here. This seems to be the only thing that we know how to do with information theoretic security, but all the other useful tasks are still out of reach. Okay, but this, okay, so what this shows is that we need computational hardness, but it doesn't actually say we still need computational assumption. So can we still show or disprove that achieving these tasks needs computational assumptions? Okay, so naturally, Ron pops up and asks, do we still need to assume P not equal NP? Okay, thank you, Ron, for the very excellent question. So this is indeed the question that for the most of the rest of the talk I'll be focusing on. So of course, we don't know how to prove this because we don't know whether P or not equal NP, P equals or not equals NP. But what I will show is some progress towards answering this question. So in particular, the way that I'm going to show this is through a technique called oracle separations. So for those of you that are not very familiar with oracle separations, formally, an oracle separation, or what we prove is just, so formally what this shows is that it will rule out a wide class of proof techniques called relativizing proof techniques. So if you want to prove that the existence of all of those quantum cryptography implies P not equal to NP, you must use something beyond, or like including but not limited to relativizing proof techniques. Okay, so the theorem that we show in this work is the following. It is possible to construct an oracle world. So where an oracle is just something that everyone can query, but otherwise does not know the description of. So it's possible to construct an oracle world where P equals NP, but computationally secure quantum cryptography is still possible. So in terms of Impagliazzo's 5 worlds, this is a world of Algorithmica, and yet you still have quantum cryptography.
What's the nature of this oracle? Is it classical? Is it just implementing?
Classical. I'll talk more about it later. This is just informal. I will talk more about it in a few slides. So more formally, what kind of cryptography did we manage to construct? We managed to construct some form of quantum pseudorandomness. And once we have this, by some existing works, we can get all of these quantum cryptography that are actually known to be existentially equivalent to each other. So this includes EFI pair of states, a commitment, oblivious transfer, zero knowledge protocols for all of QIP or P space, multi-party computation, and even stuff like undecodable black holes, which I'll not go into. Okay, so without further ado, let me talk about what is this quantum pseudorandomness object that we construct. So this object is called pseudorandom states, or PRS for short. And this object was introduced by the work of Ji, Liu, and Song in 2018. But the variant that we're going to be focusing on today is actually introduced by Morime and Yamakawa last year. Okay, so this variant is called single copy secure. So we say a quantum algorithm G is a single copy secure PRS generator if the following 2 things hold. The first condition is efficient generation. So I give you a lambda bit seed. So you should actually just think of this primitive as a quantum analog of PRG. So just like a PRG, the input is some short seed of lambda bits. And this algorithm is going to run in polynomial time, and then output some longer quantum state. So for this talk, think of the output length is 3 lambda. So you stretch from lambda bits to 3 lambda qubits. And here I require this state to be pure, which is the quantum analog of requiring a PRG to be deterministic. Okay, and the pseudorandom requirement says that if I just give you a copy of such a state for a uniformly random key, such a thing should be computationally indistinguishable from a hard random state, or for the case of single copy, it's just a random bit string of three lambda bits. So, so basically, again, this is saying that if I have a pseudorandom state of a random key, it is computationally indistinguishable from 3 lambda bits of classical randomness or random bit strings. Okay, so the reason that I require 3 lambda here is that because once we have this, then we can use a quantum analog of null commitment to get commitment, basically. So basically what you do is replacing the PRG in a null commitment with a PRS. And things more or less go through, but obviously the statistical binding will require a quantum analysis, but you can do it. Okay, and let me also just briefly comment on what is a many copy security. So basically, it's the same requirement as this, but we require something stronger. In particular, the adversary could ask for any polynomial number of copies of such a state. And still, this state will be computationally indistinguishable from the same number of copies of a hard random state, which is like a quantum analog of uniform randomness, but for quantum states. Okay. Oh, so for many copy, you are giving the same key. The state for the same key, just many copies. And in the statistical or in the random experiment, you are also sampling the same hard random state for a bunch of times.
The X is the same for the hard random state?
Oh, right. So in pseudorandom case, K is the same. In the hard random case, you have the same hard random state a bunch of times. So you sample it once, and then you give it a bunch of times.
Which doesn't really correspond to what you wrote.
Right. This only works in single copy. In the many copy, you cannot just sample a classical bit string.
So it's each of these answers, right?
Yeah.
So it must be the case that the single copy thing you cannot get statistical indistinguishability, right? Because you can put commitments and those are impossible.
Right. So here sorry, what is?
Is it obvious to see why you cannot get statistical indistinguishability?
Okay. So it's basically the same reason as classical PRG. So as long as you have stretch, then these two distributions will be statistically distinguishable, because this thing has quantum entropy lambda, at most lambda, but this thing has quantum entropy 3 lambda bits. Exactly, and an unbounded distinguisher can find out the entropy.
From one copy. So that's the thing.
Okay, yeah.
I buy.
Yeah, actually you cannot tell the entropy just here, but there is a distinguisher.
So why particularly 3 lambda?
3 lambda is just for instantiating null commitment, but really any stretch is useful. And like in our construction, we can get any polynomial stretch.
This lambda plus 1 implies 3 lambda in some way for extent.
I will say I don't know, but for some parameter regimes, we know something, but it's complicated. Yes.
Can you get the stretch for the many copy security as well, or is it only for the single copy?
Oh, so for many copy security, you don't even need stretch. Like as long as this thing is like log lambda, it will be computationally impossible. In fact, you can get commitment from as little as just log lambda qubits. Yes.
So I assume the reason there are different definitions is because like 1 doesn't imply many, or like 5 doesn't imply 6. So does it mean, if this is correct, that if you want to use it, basically at the time of usage, you need to know like what is a polynomial to generate this many copies, which means like
okay, so this algorithm G is just stateless. So for the many copy, you just feed it a key, it outputs a state, feed it another key, it outputs another state. There is no, like you don't need to tell the algorithm how many copies you want in a priori. Like the only difference is in the security requirement, not in the correctness.
You're saying you just store a short key and you can like anytime
Yeah.
something, but yeah, for security, you decide how many things you pick that up.
Right. Okay. Good. So let me go back. So now that I've introduced pseudorandom states, at least on a high level, let me go back to oracle separations more formally. So formally, before we go there, let's first recall that without, even with oracles, we can still prove the following. Like if you have a post-quantum one-way function, then this will give you a pseudorandom state, or you can construct a pseudorandom state. And once you can construct those, you can get lots of crypto applications, in particular EFI commitment, blah, blah, blah. And the formal theorem that we prove is that we show that there is a classical oracle relative to which we can construct single copy secure pseudorandom states, but P equals NP, or Algorithmica. And in fact, we have the P is in fact equals to PH in this oracle world, where PH is just the closure of NP, which is what you would expect to happen if you collapse P equals NP in the standard model. And I will also be discussing this related complementary oracle separation in the prior work proven by Kretschmer, where he showed that there is a quantum oracle relative to which you can construct many copy secure pseudorandom states. So this appears to be potentially a stronger primitive than single copy secure PRS. But in that world, we have BQP equals QMA instead of P equals PH. So before I discuss these results further, there might be a burning question. How is this even possible? In particular, how can you even collapse BQP and QMA if you have a pseudorandom state? Can we just apply the classical proof that PRG separates P from NP and do the same thing here? Like in particular, let's consider the following QMA adversary for breaking pseudorandom states. So there's a Merlin and an author. Merlin, as an unbounded prover, is just going to send Arthur what is the key that was generated, that was used to generate the pseudorandom state. And Arthur, once he knows the correct key, he can just check whether the input state is that particular pure state. And wouldn't this just break pseudorandom states, just like how you break PRG with an NP oracle? So crucially, this doesn't work. And the issue is that in order to make use of a QMA solver, you have to ask it a classical question, or a question encoded in classical bit string. However, when you are an adversary against a pseudorandom state, what you get is the quantum state, psi sub k. So, and there does not appear to be a way to transform a quantum state into a classical question for QMA. So that is the issue. So even QMA only considers solving classical problems, albeit with a quantum computer, and it does not appear to be helpful. Indeed, we'll see surely more formally how this works.
I guess one question here is if you had two copies of psi k,
Mm-hmm.
you could in principle send one to Merlin and ask, I mean, it wouldn't be a QMA protocol exactly, but like you could send one to Merlin, ask Merlin to tell you a likely key, and then check, or maybe send if you had several copies, right? Send a bunch of copies to Merlin.
Right.
For the key, and then check the one reserved copy. Does that type of protocol rule out any class of separations? Or I'm just trying to you mentioned that the
Right, but
parallel
Good, good, good.
work that
Even if we,
there's a different kind of oracle, and I'm
yes,
wondering
yes.
if there's some relationship.
Yes, but even if you consider QIP, like I give you unlimited number of rounds, right? In a QIP protocol, the author just have a classical input. It does not have quantum input, whereas the adversary here, again, in the PRS experiment, does have a quantum input.
Yeah, I understand.
So,
it sort of doesn't, like the protocol where you send some of the states to Merlin and get an answer, that does not correspond to some like classical language,
no.
right?
Because the verb
Right.
is supposed to be classical in every
Yeah.
QIP.
Well, and also, it just like there's no bit strings, right? There's no, the inputs are not strings. So like, I'm just saying it doesn't even like there's just doesn't even make sense to talk about a classical language.
It's like this protocol works, right? Like
Right.
it actually is sound and everything. It's just like
Yeah.
syntactically.
Right.
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 And so, but what I was wondering is if like, does the fact that that protocol exists kind of tell us anything about the types of separations one might be able to get or something like that?
Good, I'll talk about it later.
Sure.
But at least it does not appear, if you just have QMA, it does not appear helpful. Even if you're giving me QIP or P-space, it does not appear helpful.
So can I ask you something else? So if you have many copies, right,
Yeah.
you could potentially do some sort of shadow tomography, classical shadows, right? Which I think some version of it we know how to do.
Yes.
And then you get a classical statement which you can.
Right.
So presumably, is it plausible that the version of Kretschmer's statement, right, relative to a classical oracle is just impossible to prove? You know, like he has this trade-off, right?
Okay.
Many copy versus one.
Maybe hold on to your question. I'll talk about Kretschmer in a bit. Okay. So before we go to separation, one more thing, which is that so our work or this classical oracle separation also gives you something non-trivial. In particular, we give a first non-trivial construction of pseudorandom states. In fact, it's the first construction of any quantum cryptography that is whose security is separated from the existence of one-way function. And indeed, like in prior work, there are also candidates, but there are no separations proved. So this goes back as early as 2005, where Kawacki et al. Show that, so they conjecture that if you assume hardness of a particular quant state distinguishability problem for a family of permutation states, whose hardness you can show is implied by graph automorphism, then you can get things like quantum public key encryption. There are also construction of quantum auxiliary input EFR commitments from complexious separations, but just like classical auxiliary input cryptography, in order to make use of them, you first need to do an inefficient or pre-processing so that every party in the protocol needs to have a copy of this non-uniform advice, and then you can do crypto. And then there are also some folklore construction that maybe you can get quantum cryptography from random quantum circuits, or even by reverse engineering the dynamics of wormholes. But as I said, all of these are just, so none of these have, so some of these does not even have security proof, but none of these are actually separated from P versus NP. Yes?
So just maybe you talked about it. For the positive implications of PRS, what is implied by one state PRS versus many state, like commitments and all those things? Do they require
All of those implies commitments.
even one time? You can give you
Even one time.
You can build all those positive implications, just need one time PRS. You don't need polynomial.
Yes, yes.
Is there anything then which we don't know how to do from one-time PRS, but we know how to do from polynomial PRS?
Encryptions, for example. Right. Okay, so let me just first give you a brief sketch of how Kretschmer's separation work, and maybe this will answer your question. Before I tell you how the proof works, let me first give you an intuition of how the separation works. So the intuition is that for many copies pseudorandom states, actually, without talking about pseudorandom state, let's talk about a truly hard random state, an information theoretic quantum analog of uniform randomness. If I have a true hard random state, then it is known that such a state is extremely entangled. So think of it as this, but it's entangled. Okay, so what's the crucial observation? The observation is that a hard random state satisfies an extremely strong notion of concentration, sometimes also known as Levy's lemma. And from using that lemma, you can see that it is actually impossible to extract any useful classical information from a hard random state, even if you have a lot of copies or polynomially many copies of such a state. Therefore, if I really have a hard random state, it appears that it will be impossible to reduce any problem about this state to any problem about just classical information. So this is the intuition. So the proof sketch is actually pretty simple. So the quantum oracle that Kretschmer considered is just a hard random oracle U and a p-space oracle, similar to Impagliazzo-Rudish. But instead, you have a hard random oracle, which is a quantum random oracle. Okay, so to construct a PRS, it is pretty straightforward. You just call the hard random oracle. It is basically very similar to how you will get a pseudo-random function from in the random oracle model. And this will be secure even if you have a p-space oracle, because this p-space part is actually independent of the random oracle. Okay, and how do you show BQP or QMA collapses to BQP? Using the concentration property that I mentioned before, what you can show is that any QMA machine, even those that queries the hard random oracle, their output is actually essentially independent of which hard random oracle you are giving it. And therefore, the idea is that we can just remove this hard random oracle from this QMA machine. And so once we do that, we can just use the p-space oracle to decide this QMA machine, even like after we remove the random unitary.
So what does a hard random oracle do? I can input like lambda bit string, and it'll output some 3 lambda bits.
Yeah, think of it as a hard random unitary. So you feed it any quantum state, it will give you some hard random. It's like a PRP, but for quantum states. Well, actually, maybe I should say random permutation, not PRP. A truly random permutation. Okay, so you may say, okay, maybe some of you may say, okay, this seems pretty good. So why do we even bother to prove another separation? Why isn't this already pretty conclusive? Well, first of all, this proof is kind of cheating, because one-way function, if you are trying to construct a one-way function in that oracle world, you are stuck because there is a quantum oracle, and as a classical machine, you can basically never access the quantum oracle, let alone a hard random oracle, right?
The algorithm, the computes a one-way function could access the oracle, it just cannot output quantum states, right?
I mean, but the definition of one-way function actually asks you to use a classical algorithm.
But it seems fair to change it to say, you can use a quantum algorithm to compute it.
Okay, yeah. You can even say, let's say I use quantumly evaluatable one-way function. Then it might be less cheating, but there are also other issues. So the second issue is that if you use a quantum oracle separation, it actually rules out fewer proof techniques than a classical oracle separation. In fact, it is shown in the work of Aronson that there are a certain quantum oracle separation that fails relative to any classical oracle. So indeed, they are weaker than classical oracle separations. And the third complaint or weakness is that that separation that I just showed you is somewhat contrived to put this complaint more formally, it is somewhat uninstantiable, right? Because it uses a hard random oracle. But how are you actually going to heuristically instantiate a hard random oracle? We don't know. In fact, even to construct a pseudorandom unitary, which is a hard random oracle analog of PRF, this is still an open question since the JLS 5 years ago. Yes?
Sorry, I'm just curious. The notes question. I thought that hard random oracle is just like a random oracle that you can pair in superposition, but you're not saying.
No, that's QROM, or quantum random oracle. This is hard random oracle. It's a unitary. Like even if you feed a classical bit string, it will give you back a hard random state.
Also, it's like for any classical bit string, it gives you this hard random state, and you can ask superpositions or whatever.
Sure, you can ask in superposition, then you will get a superposition of those states.
And the hard random state includes where you're saying it's like more powerful than the random state because you don't have to measure it.
Yeah, in some sense. Of course, if you measure, you'll get a close to uniform bit string, but it will be, before you measure, it's a pure state.
Would it be instantiable? It seems circular, but would it be instantiable given single copy PRF?
So we know how to construct PRS from PRF or one-way functions, but even with one-way function or any reasonable assumption, we don't know how to construct pseudorandom unitaries. So this really appears to be a much harder thing to construct.
Oh, I see. Okay.
You're right, so going back to your question, even if I have PRS, I don't know how to construct these.
Right. No, I had misunderstood what a hard random oracle was.
Okay.
Now I get it.
Maybe a hard random state is somehow not even very physical.
Well,
That's what we call instantiate.
okay, I'm not a physicist. Let's leave that discussion offline. Okay, the final complaint is a minor point, but still. Our work gets P equals NP, which is commonly known as Algorithmica, whereas that oracle separation can only get BQP equals QMA because you use a quantum oracle. And BQP equals QMA is not called anything by Pagliazzo. And formally, these two statements are also incomparable. So like we have oracle separations between each direction. Like P not equal to NP does not imply that, and vice versa.
Did you try querying Russell and get a good name?
I think next week is Russell's 60th birthday.
No, it's today.
Oh, it's today.
Yeah.
Okay.
You can call him. Okay, so these are the complaints. Okay, so I think Ron also saw this oracle separation and thought that, well, this seems not very convincing. Like, do you have any comments? Okay, I will make a comment for you. Clearly, hard random oracles are even more structured than random oracles, right? Such strong concentration you cannot get from random oracle. Okay, so now let me really get into our separation. Actually, before we go to separation, let me first tell you how the construction will work. And in fact, this is a construction that you can use even without oracles. So the starting point of the construction, our construction is a construction called binary phase pseudorandom states. So how does it work? So for now, we are in the standard model without oracles. So because I'm constructing a PRS, I have some input, which is a short seed of lambda bits. And then the PRS is going to be given by a family of Boolean functions mapping n bits to a single bit. So for this talk, think of n as just like the output length. So n is 3 lambda. So you have a 2 to the lambda possible 2 to the lambda many Boolean function mapping 3 lambda bits to 1 bit. So here's how the construction works. You start by initializing n qubits, or 3 lambda qubits in O0 state. You apply Hadamard on all of them, which will give you n plus qubits. Or if you look at this in the computational basis, this is essentially a uniform superposition over all the computational basis states. And then I'm going to do what's called a phase oracle for the Boolean function. And what that will give you is basically this state. So for each computational basis state, when you query the phase oracle, you will get back a phase -1 if the Boolean function outputs 1. Otherwise, you get a phase +1. So in the end, you get a uniform superposition over X, but the phases are ±1 depending on the output of the Boolean function. That's it. This is the construction, and you output this state as the PRS. Okay, so this construction actually is proposed back in the first work that introduced PRS by Ji, Liu, and Song. And they did not prove it secure. It is only proven secure later in the follow-up work by Brakowski and Shmuley. What they show is that if these f's are just random functions, then they are indeed pseudorandom states. And by a standard argument, if you replace this random oracle with pseudorandom function, they are still computationally secure. So that's how you get a PRS from one-way functions, for example, post-quantum one-way functions. So since we are investigating the question, maybe one natural question we'll ask is, maybe this is still secure even if P equals NP. Unfortunately, in this prior work by Kretschmer, it is actually, he also shown that there is an attack given an NP oracle. So in particular, if you have a quantum algorithm that can query NP oracle, then you can break this construction for any efficient F. So in order to make our theorem work, we need to do something more. And a natural thing that we are going to try is just to do the same thing but more times, similar to Luby-Rakoff. So this is what Scott Aronson calls the Hadamard phase cocktail construction. So how does this work? Again, you start with O0 state, and then you do Hadamard, and then you apply phase oracle for a function f sub 1. What you are going to do next is just to do this a bunch of times more. So you do Hadamard again, do phase oracle for a different Boolean function f2, so on and so forth. And let's say we do this for t times for t Boolean functions f1 to ft. And I'm going to give this construction a name called T4 relation states for f1 to ft. OK, so just restating what we've already known about binary phase state from the last slide, we can prove that, or like basically get a corollary that if I have a random oracle using f1 to be h of k input, so this is like a 3 lambda bits here, then this is a 1-4 relation state, which is essentially equivalent to binary phase PRS. And this is a PRS that is secure against BQP. So what we show in this work is that if I do the same construction, but for 2-4 relation state, so just do it one more iteration, and I'm going to pick f1 to be h of k1, some input, and f sub 2 to be h of k2, some input. Then what we can show is that instantiating this 2-4 relation state, it is in fact a single copy secure PRS against BQP that can even query a pH oracle. In particular, this adversary can query any pH question about the random oracle. So unlike the separation that I showed you before, this pH can even query the random oracle. So it's like a BQP to the pH to the O. So what we show is that even if you can query any pH statement about the random oracle, such a construction still remains secure for single copy. And the reason we only get single copy security is quite technical. We believe this construction should be, in fact, multi-copy secure. It's just that we don't know how to prove it. There are some technical issues.
How important is it?
Yeah, sorry. Yeah, here it's a random. Starting from this line, every H is random oracle. No more Hadamard. Sorry. Yeah, sorry.
But this question probably doesn't really make sense, but how important is each is a random oracle? I cannot substitute it just directly as a PRF, but I'm wondering that if you can replace it with any, classical function, would those results still hold?
Wow. I'll talk about it later. Yeah, very good question. I'll talk more about it later.
So you don't, in particular, you don't know an attack against this with given many copies. You don't know a way to kind of.
Right, exactly. Even if I give you, this state, for example, if I instantiate with SHA-3, and I also give you a p-space oracle, or in fact, I tell you p equals p-space, how do you break this for many copy? We don't know.
So in particular, the conjecture is that there might be a common generalization of Kretschmer and your result. Like that's what it would.
Maybe. Yeah. Yeah. So I think at this point, when Ron saw this, he was reasonably convinced that okay, maybe quantum cryptography does exist in Algorithmica. Okay. And just to mention that we also introduced a conjecture about T4 relation. And under that conjecture, we can show that such a construction, when you instantiate essentially the same thing, then it will be, in fact, multi-copy secure even against BQP to the pH. But we don't know how to prove it.
Would we know about one correlation is broken? So you said.
Yeah, so for one for relation, if you have an NP oracle, you can break it.
Wait, even if H is random oracle?
No, so the statement is that for every efficient function f that you plug into one for relation state, if you have an NP oracle, you can distinguish it from.
It seems like whether you're using a true random oracle versus you're using a real binary function, that seems to.
Okay, good. So, good. Sorry. So even for a random oracle, if you have an NP oracle that can query the random oracle, then it will also be broken. And here, for true for relation state, I'm considering an adversary that can query pH that also queries the random oracle. So it is indeed like, for the same adversary, it can break one for relation state, but not two for relation state. The exact same.
Can you give us a sense of how the one correlation state is broken with the NP oracle? Is that complicated to explain?
Okay, so the intuition is that if you go back to one for relation state, this output is actually related to the output of a certain algorithm called Simon's algorithm. And once you have that, you can make some observation that you can use this to essentially find collisions in the random oracle. And once you have enough collisions of the random oracle, you can uniquely find you can statistically find the key that corresponds to the K, and then you can indeed like. Okay, yeah, sorry. Here it's multi-copy. Like for this attack to work, you need many copies of this state, because just getting one collision might not. Does not statistically determine the key.
But the claim is that there is a single copy attack, right?
Yeah. Sorry. Yeah. I don't know the single copy attack, but it's broken for many copies.
So is it right that I can say that for some PRS states that it does require P naught equals to NP?
Right. For this, in particular for this construction, if it's secure, it implies P is separated from NP.
So your point is there are other PRS states that.
Exactly. So the true for relation state.
So just to make sure I understand, the statement you proved, right? You could have potentially proved it with
No.
Yeah, you could have proved it with the.
Yeah, if you only restrict it to single copy.
Yeah.
Right. It is plausible, but I don't believe it should be true. Okay, yeah, so what is this, why do we call this correlation state? It turns out to be related to this correlation problem. So the correlation problem is essentially, I give you two Boolean functions that are sampled according to some distributions, and I want to ask you to distinguish how I sample these functions. So in the first case, I sampled two functions such that the Fourier transform of f is correlated with g. So the Fourier transform of f under the standard binary field. So this is also called f is being correlated with g. And the second case is just f and g are uniformly random functions. So with high probability, they are not correlated. So this problem was introduced to show a candidate that separates BQP from pH. And indeed, in the breakthrough result by Raz and Tao, it was shown that this problem is in fact hard on average against pH. And in the prior work by Aronson, Ingram, and Kretschmer, it is shown that a variation of this problem called OR of correlation, so the OR function composed with correlation, such a function is in fact hard against BQP to the pH query algorithms. And this will be like the starting the starting point of our security proof. So the idea is that we want to basically reduce the security of two correlation state to this problem. So I don't have much time left. So let me just tell you how the hardness property looks like. So in this work, we actually introduce a hardness about a classical function that we call hardness of shifted correlation. So what is this hardness? You can think of it sort of similar to the PRF security. So just like PRF security, you have the PRF family, or here I have a big hash function, big H, and the adversary is going to distinguish two oracles, either a pseudo-random oracle or a truly random oracle that is sampled related to this big H. So in particular, I say big H is hard to find shifted correlation if I give you quantum query access to little h, and your task is to decide whether h is sampled in the pseudo-random experiment or the random experiment. So in the pseudo-random experiment, this little h is sampled such that there is some key in the big H such that HK0 is correlated with HK1 XOR little h. And in the second case, this little h is just a random function, just like in the truly random experiment. So, so in particular, in the second case, it will be true that with high probability, there is no key that HK0 is correlated with HK1 XOR h. So think of this little h as being the hidden shift on the second part of the function, and you want to find if there are a pair of functions that are actually correlated. Okay, so what we show in the paper is that if you have such a hardness, then this hardness will give you the single copy security of a true correlation state for H. And on the other hand, we also show that if you just give me a random oracle, then this oracle does indeed satisfy this hardness even against BQP with a pH oracle. And the way we do this is to reduce this hardness to a variant of the average case hardness of oral correlation. And actually, in order to make this work, we have to consider a slightly different correlation distribution that is discretely defined, which might be of independent interest. Okay, so that's all I wanted to say about the proof. So let me wrap up and talk about what are the implications. So basically, we show that there is some hardness for a classical hash function called hardness of shifted correlation that satisfy the following properties. The first property is that it seems to be useful for constructing quantum cryptography, like single copy pseudo-random states. the second property is that it's a plausible because we show it is actually true for random function. In fact, this hardness is hard even for BQP with a pH oracle. And finally, in the black box setting, this hardness seems to be weaker or at least independent from P not equal NP, or in fact, P not equal pH. So plausibly, we can just instantiate this two-fold relation construction with a cryptographic hash like SHA-3, and it is plausibly secure even if someone discovered a proof of P equals NP. Okay, so I also gave this talk last week in Simon's, and for those of you that have not seen the talk, here's a joke about the Impagliazzo's 5 worlds, and hopefully this joke is even better the second time around. So here we have a beautiful illustration of Impagliazzo's 5 worlds. So the takeaway of our work is that basically our work is like a Thanos snap, and they don't feel so good, and they're gone. Okay, so going back to the question that I raised at the very beginning, does cryptography actually need computational assumption? And what our work shows is that this question seems to be actually independent of Impagliazzo's 5 worlds. And the cryptography that I talk about includes MPC, encryption, authentication, etc. Certainly, they are independent in the relativized world. Of course, you may also ask, are there simply no complex implications we can prove for any quantum cryptography? Actually, we do know some implication. For example, in Kretschmer's work, it is also shown that if you have many copy secure PRS, then you can actually separate PP from BQP. And this the way you prove this is indeed, as Vinod said, is using classical shadows. And so basically, the idea is that you're going to do classical shadow on PRS, and then you're going to ask a PP oracle to try to break this construction for you. But this only works for many copies, because classical shadow needs many copies. Okay, and in an upcoming work, we used an observation about a recent result by Mecker and Yuan to show that if we have any quantum computational falsifiable assumption, so what this is that it is a quantum generalization of a falsifiable assumption. So you have a security game with a quantum adversary and a quantum challenger. And if this security game is information theoretically broken but secure against quantum adversaries, then we can basically show that we can separate a unitary version of P from unitary version of P space. But unfortunately, this does not mean that you need computational assumption, because for all we know, these two classes are just different unconditionally, and we haven't discovered a proof yet. Unlike classical P versus P space, which is a long-standing open question. Yes?
What does it mean to have a unitary version of P since P is classical?
Unitary version of BQP, quantum P. Yeah. Okay. So let me conclude with some open questions. The first question, does single copy secure pseudorandom states or the weaker primitive of EFI or commitments? If we have those, can we still separate or reduce them to non-barriers like P versus P space in the decisional language, which is a hard open problem, unlike the unitary version, which we just defined. Or can we also prove that maybe there are separations? Like, can we prove that they can exist even if P equals P space? And the more important question is still the question I raised at the very beginning. Can we just prove that they exist without using any computational assumptions? Or are there other barriers that we don't know that we'll run into? Finally, this is more general, a broad general direction. We would like to better understand the complexity of quantum tasks, including but not limited to breaking quantum cryptography, where we have a separation. Also, there is also, I forgot to put in the slides, but there is also a Ranshoven question, which is, give me a candidate of a simple hash function to instantiate to a correlation state that's plausibly still secure against P equals NP adversaries. But don't use any complicated hash function like SHA-3. Use something much simpler. Okay, so that's the talk. Yeah, thanks. Right. You can say like at the first part of the talk where I showed there is a QMA style protocol that breaks pseudorandom state. You can try to define maybe a version of QMA where the author actually gets a quantum state as input. Then you will separate that class from the BQP version of that class, basically. Yeah, you can define it and you can prove the separation. But
it would be like the worst case analog of PRS, kind of. Like it would be P not equivalent to one of these functions would be like PRS, would be this problem of PRS.
yeah, I'm not sure. Yes.
So, Impala's 5 worlds have proven to be a really useful kind of categorization for just thinking about the implications of, the possible implications of different types of hardness within NP. Does it make sense to try and identify some number of sort of similarly representative worlds? They don't have to cover everything, but that somehow capture the major categories that one might try to separate and understand. It doesn't
Yes,
have to be complete,
yes.
right? Like the Impala's 5 worlds don't cover all
Exactly.
the interesting complexity versions we could add, right? It just somehow really nailed like a bunch of fundamental variations.
It came at a time when we knew just enough about what we can do in cryptography, right? So there's a sweet spot when we figure out a little bit more of what we can do in quantum crypto.
Maybe, yeah. Although it feels like we're kind of getting to that, starting to get. I mean, yeah. So who knows? But like it.
There are a bunch of cryptography. I think it's a great question.
Yeah.
I think there are a bunch of cryptography tests that we don't know how to do today, from commitment, invite, all those things. All kind of, there are stuff, right? Defining integers in cryptography.
In any case, it's a great question.
So maybe there's separation.
Right. Yeah. So again, the idea is not like a total categorization of everything we know, but just like sort of a here are like.
Yeah, I think we need a quantum version of Russell. I mean, the person. At least person.
He's already quantum. We all know. We're good.
Okay, but I think like maybe the quantum complexity is not quite ready to make a reasonable categorization yet. At least I don't know how to give you a small number of worlds. maybe in 5 years.
Well, don't wait too long. Because, right now, if Russell were to write down that same category, thing, he'd have like a lot more worlds. Some of them are known to be mutually incompatible. Like it would be like a lot messier.
With that. Yeah, that's
Right.
Yeah.
Maybe, I don't know, to follow up on Daniel's question, and maybe I'm misunderstanding stuff, it appears to me that our version of like quantum complexity classes, they are non-composable in a sense that we say, oh, let's look at classical problems because good guys are always classical, but let's see how can quantum algorithms solve it. Classical input, basically classical output, but for some few separations, the subtlety was that you actually need to give a really quantum input and you cannot use those oracles. So my intuition seems to imply, if I understand correctly, that these quantum complexity classes are defined incorrectly. They're kind of uninteresting because they're non-composable. So maybe the right thing is kind of what Daniel is saying, like to define also complexity classes to be like everything quantum. Don't like say something classical and then things kind of don't compose, and then you get results which look interesting but are kind of stupid. I mean, I don't know. Is it maybe this is like a way out, kind of to say we define quantum complexity classes incorrectly?
Excellent question. I have a backup slide for that. Yeah. Yeah, there are actually some works studying exactly that. At least this work that have studied, maybe we can define quantum complexity classes using quantum inputs and outputs. And I do believe that. Okay, and we are beginning to see that there are interesting theorems starting to be proven about them. So indeed, maybe people before, like they really focused on solving classical input problems because that is, at least in the past, what people cares about solving using quantum computers. But indeed, when you look at the bigger picture, there are things, computational attacks that are not captured by our current language of complexity theory, like breaking quantum cryptography. We show you cannot capture with QMA. There are also other things like quantum algorithmic measurements, which is like doing quantum experiments but with quantum computers. Those things you can also not capture with today's complexity theory. So yes, this is something complexity theorists are working on.
Results here, so like in any of those papers where everything is kind of quantum, does sanity come back? Everything is composable. There are no like these weird looking results. So
yeah, I'm not sure about composability, but that's an excellent question. I think it's still pretty early for this line of research.
I think we'll, in the interest of time, yeah, there are more questions, but we'll take them offline and go to the break, and we'll resume on time-ish at 11:30.
Okay.
Here, he's done amazing work since then, and she'll tell us a little bit.
Thank you, thank you. Super happy to be back. Thank you for inviting me. Of course, today is not about me. When Adam invited me and said this is Run themed, I felt like I'm so compelled to come. Congratulations, Ran. You've made it. Made it to what? Let's not specify. Yeah, so I am going to, what better way to celebrate Ran than to talk about interesting research. And that's what I learned from Ran, and I'll still feel more about him at the end. But most of the talk is going to be technical. Feel free to ask me questions. I know this is a crowd that asks a lot of questions. I'm very happy to skip a few technical slides at the end. All right, so this is a joint work I'm doing with Marshall Ball at NYU, Hanjun Li, my student at UW, myself, and Tianren, who was a a PhD student with Vinod, and then did a postdoc with me. And now at Peking University. All right, so this talk is really about the bread and butter of cryptography, which is Garble circuits. What it is that it gives us a way to efficiently transform a Boolean circuit into a garbled form, which we denote as C hat, together with several pairs of keys, AI and BI, one pair for each of the input label, for each of the input bit. Okay? And what is it good for? First of all, given the Garble circuit together with the input label chosen according to the value of the input. So if xi equals to 1, then we'll choose AI. If xi equals to 0, then we're going to choose bi. So this is sort of the collection of keys that are chosen according to the input. With these two things, sort of one is an encoding of the circuit, the other is an encoding of the input, we can evaluate the circuit and obtain the output, C of x. And furthermore, it reveals no other information except for C of x. So here I'm considering a version where the circuit is public, and we are only interested in hiding the input. And this is captured by saying there's a simulator given the circuit and the output. We'll just be able to simulate some fake version of the Garble circuit and the input label that is indistinguishable from the real. Okay, so Garble circuits really needs no introduction. Sorry for boring you. But one more thing I want to emphasize is that the input keys and the labels should be really short and independent of whatever complexity parameters of the circuit. And furthermore, note that the input encoding function, which is choosing which key to use, is very decomposable in the sense that it operates one bit at a time. And furthermore, it is very simple. It is, in particular, an affine function. Okay? T is the length of the key length. Okay. All right. So Garble circuit is really everywhere an amazing concept proposed. And its generalization called randomized encoding is really used day by day. And there are so many different areas I could not even list all of them. And to the extent that when we use a Garble circuit in a paper, we don't even pay attention, right? It's like, yeah, there's some Garble circuit there going on. Doesn't worth mentioning. And the universal usage of it is thanks to the two properties. Very simple garbling algorithm. Typically, we leverage the fact that it's a low depth function, even though your original circuit could have arbitrary depth. It could be as low depth as to NC0, constant depth. And the second factor we often use is that it has very simple input encoding. That input encoding is short, it's decomposable, and it's affine. Okay, so what techniques do we have for implementing Garble circuit? Once I mention it, you immediately think, oh, Yao's Garble circuit. Yes, this is something that you probably learned in undergraduate crypto class. And it is a method which we use encryption schemes to encrypt the truth table of each of the Boolean gates. And if it's a binary logic gate, then it will have 4 entries, and we permute them. So I will call this the encrypted truth table method. Invented by Yao, it is really such an amazing technique, still used every day. And recently there has been a lot of amazing optimization on this method because we are achieving encouragingly practical efficiency of Garble circuits. And the state of the art is that we can actually reduce the number of ciphertexts needed down to 1.5 per gate instead of 4. Okay, so this is the level we care about. It's that we care about that constant. We care about that constant reducing from 4 to 1.5, and this is achieved using a sequence of clever ideas and work. So what other techniques do we have with Garble circuits? Maybe we're just satisfied with encrypted truth table. So in the literature, we have extended encrypted truth table to also manage to garble Turing machine and run machine. Okay? And the basic format, the size of the garbling is going to scale with the worst runtime of the RAM computation. However, if you use very strong cryptographic tools such as indistinguishability obfuscation or functional encryption, you can actually shrink this garbling down to the size of the RAM computation, independent of its runtime. But by and large, these are based on encrypted truth table methods, I would say. There is a completely different, much further away technique, which is giving us reusability in the sense that we can garble the circuit once and for all, and that garble circuit can be used with multiple input encodings, and while the input encoding is still short and small. And this really relies on the technique of fully homomorphic encryption, attribute-based encryption. It still uses the garble circuit, but the computation is carried out using those homomorphic primitives. So I would say this technique is somewhat far from encrypted truth table. But more or less, that's what we know. These are the different methods we know how to garble. So the question, oh, not the question yet, but definitely I think we all agree that encrypted truth table is still the most widely applied technique. So the question today is, can we do it in a different way? And in order to explore different techniques, I'm going to look at a different problem, slightly different, to force us to use different technique. That is to garble instead of Boolean circuit, now arithmetic circuit. Their circuits were composed of addition and multiplication gates. They do arise pretty naturally in real life, such as in scientific computing, in machine learning, in crypto systems. And for different application, we might care about different underlying ring, right? So for the purpose of this talk, we're going to mostly look at integer computation and integer computation mod P. But arithmetic circuit, you can also think about polynomial ring or any other ring. Why do we care about garbling arithmetic circuit, given that we already have a baseline solution, which is you can always take all those, find a Boolean implementation of those arithmetic operations, convert this arithmetic circuit into a Boolean one, and then just apply the encrypted truth table, right? But the question I want to ask is, can we not do that? In the sense that, can we garble arithmetic circuit without Booleanizing this computation? And why? Because sometimes that bit decomposition is expensive, undesirable, or even possibly unavailable. Like, it's possible that your input is already encrypted using some arithmetic encryption. Hence, you don't have the bit decomposition available. But more to me, perhaps this will really force us to avoid the encrypted truth table method, because the underlying ring may be exponentially large, and the truth table for each individual gate is already exponentially large. There's no way that I encrypt each of the entry, right? So this is a good test bed for me to invent, for us to think about new techniques. And when we do so, perhaps we will reach out some of the goals that we care about, such as efficiency and modularity, in an unexpected way. Okay, that would be the best outcome. So what do we know about garbling arithmetic circuit? So this question was proposed by Appelbaum, Ishai, and Kushlevitz in 2011, where they defined it in the following way. Still, we would like to first convert now an arithmetic circuit, given with the description, which is a sequence of addition and multiplication gate, transform it into a garble format, and together now, one affine function for each input wire. This affine function is still defined by two keys, which are the coefficients, and they can be a vector over the ring. And now an input label is going to be the evaluation of this affine function on the input value. The same correctness and security requirement, given the garbled circuit together with the input labels, we should be able to learn the output of the computation Furthermore, that's the only thing that is leaked. Okay, so everything can be simulated using just the circuit and the output. Here again, that we want the input labels to be short, right? The affine functions should have a dimension that is independent of the circuit complexity. And by definition itself, the input encoding is still decomposable and affine. So if we look at this definition and think about with respect to my goal, well, this definition basically forces us to treat the input values as a whole instead of bit decompose it, because all what you're going to get are those affine evaluation of the input value over the ring, right? However, it does not exclude the possibility that the Garble circuit does something that mimics bit decomposition inside and then get the bit representation and furthermore apply the encrypted truth table method. So it's a very nice definition, but for my purpose of avoiding or finding alternative methods different from encrypted truth table, I'm going to ask for one more property, which is that I want the gobbling algorithm and the evaluation algorithm to be black box in the implementation of those arithmetic gates, addition and multiplication. I want to emphasize that this is actually different from fully black box, being fully black box in the ring, which means that I would not have, we would not be able to leverage any property of the ring, and that is actually ruled out.
What's the difference in fully black box? I potentially don't even know the characteristic of the ring or the size of the ring or something, but you are going to use this information. Is that?
Yeah, for example, I would allow my Garble circuit to say if I need to do, for example, if I want to use LWE or something like that, there's a concept that I can sample small elements in the ring.
So it's more than the characteristic, it's something.
Yeah. And for example, if I obtained 2 ring elements, which potentially I will do a comparison. However, this usage of the comparison is complete black box. Like
Comparison doesn't mean equality, but somehow there's a norm defined on the.
yeah, so for example, in ZP, I could compare if I got a ring element that's bigger than P over 2 or smaller than P over 2. However, that concept doesn't exist for a general ring. And that is ruled out in the fully black box usage.
So like before you said this property, right, there was at least a feasibility result that you could construct arithmetic Garble circuits, but with this property, it's not clear that it exists, right?
It does it.
You could be decomposant, you could do Fermat.
Yeah, so this property is going to exclude solutions that internally does bit decomposition. But there is another arithmetic circuit, arithmetic gobbling construction by the AIK work that does not do bit decomposition internally. And what they can manage is that they can handle B-bounded integer computations. So this means that we're doing addition and multiplication over the integers. However, the magnitude of the wire values is, in the worst case, doubly exponential in the depth of the circuit. And hence that this will quickly become like not efficiently handleable. And therefore, there is a constraint that you're given with the promise that the computation C and X, all the wire values are bounded by a known upper bound B. And this is what is called the B-bounded integer computation. If you know that upper bound, then there is an arithmetic way of gobbling these integer circuits, assuming LWE. In the work of AIK, they indeed provide an alternative construction that does exactly what I mentioned, that it will internally bit decompose using the Chinese remainder theorem, and therefore they can apply Yau's Garble circuit essentially. Okay, so this is what we know about arithmetic circuits, about how to gobble arithmetic circuits so far.
So could this black box definition be sort of restated in terms of complexity by saying the size of the Garble circuit is independent of B? Or
The size of the Garble circuit is actually going to depend on B. Yes.
But linearly or logarithmically, right? Because if you did the bidding.
Oh yeah, of course, logarithmically.
Okay, good.
but that's the case maybe here also.
Yeah, it's the case here.
But if you try to bid, map numbers to bits, you would probably need to do it's still logarithmic.
Still logarithmic, yeah. All right, so what we do in this work is we extend what we can do with gobbling arithmetic circuits. We can gobble these three different modes of computation. One is same as AIK, B-bounded integer computation. The other is we can now gobble ZP computation for any modulus P. And the third is we propose a mixed integer and a Boolean computation model where your circuit can do integer arithmetic, but then also do the bit decomposition followed by some Boolean computation. And you can switch different modes arbitrarily. For those models, we construct it using either learning with error or Palier groups. And for the B-bounded integer, we improved efficiency comparing to the AIK construction. In particular, we'll get constant rate according to a definition of rate I will tell you next. For ZP computation, we are the first construction that is satisfy the property I just mentioned, that is black box in the implementation of the arithmetic operations. And for mixed computation, this model really we think captures more realistic computation, and we also have not practical efficiency, but better efficiency than using the brute force like a bit decomposition.
Just to make sure I understand, there is a feasibility result for all these. It's not about feasibility. You look at the solution, it's different and interesting somehow.
So the feasibility solution means either you're converting to Boolean circuit and use YAO, absolutely, or you can use the AIK method. AIK in some sense define a bit decomposition because they are going to internally do Chinese remainder theorem and bit decompose, right? So AIK, that construction is going to give you these models as well. But the difference is, in some sense, I feel it defeats the purpose of doing arithmetic gobbling, in my idea. It only guarantees that you're not going to access the bits of the inputs, but why do we want to arithmetic gobbling? Because we want a natural way to gobble arithmetic circuits, not like bit decompose that's inefficient, and that's what we achieve.
And one thing you could do is you could restrict the access to the field by saying you can only use black box addition and multiplication and so forth, but then you're saying there's an impossibility.
Right,
So you can't,
right. The best idea is to not use any property of the ring at all and just get a fully black box construction. That way that with one construction, you actually get arithmetic gobbling for every possible ring. And that dream is ruled out. We have to use some property of the ring, and indeed we do.
Is it easy to see why that's impossible?
It's a very smart way, like you can do some derivative of the attack is gonna take it and then do some derivative of the gobbled elements. I don't have a succinct description of it. It's a very, very cute. However, I don't know to what extent it really hinges on the specific rules on how you can access the ring.
So something like computing x to the p minus 1 in ZP would be considered black box or not black box in your?
X to the p minus 1?
Yeah. Is that what's not black box?
yeah, you can. I think in the impossibility result, you don't even know the characteristic of the field.
Right, it would not be fully black box,
It
but
won't
it
be fully
would fit
black box.
Yeah,
Rachel's model of black box.
yeah, yes, it will fit my model of black box, yeah. Okay. All right, so let me tell you in more detail what we achieve. I said that we get some version of constant rate garbling. So what is that rate I'm talking about? We define the rate as the ratio between the size of the garble circuit and the input label. This is the total bit length of what you need in order to start the computation, versus the size of the circuit, which is the number of gates, multiply with L. What is L? L is how many number of bits you need to represent the wire values. In other words, absolute value of C times L is the size of a computation tableau if you've written it down in the clear. Okay, so this is a specific notion of rate. It does make sense when we consider those gate-by-gate approach of garbling circuits. And why in particular multiplying this L comparing with the computational tableau instead of comparing with just the number of gates in the circuit is because that if I have a gate which is a Boolean gate versus I have gate with string integer and multiplication for very large integers, the complexity is different, right? And it seems natural to us that to allow the garbled version to also scale with the complexity of the gate itself. Of course, one can dream bigger to have like, and indeed that some prior work kind of do not even compare with the complexity of the computation tableau. But I will argue this is a relatively natural notion of rate. So under this definition, the rate of Yale's garble circuit is lambda, the security parameter, the size of each ciphertext inside the encrypted truth table. If we transform an integer arithmetic circuit into the Boolean version using the baseline, then we'll get an asymptotic rate of log L times lambda using the asymptotic fast multiplication, integer multiplication. So can we do better than that? Our first result is assuming DCR over Palier groups, then we can get an arithmetic garbling of B-bounded integer computation with constant rate when the integer length is comparable to the Palier key length. Okay, so that is log of the Palier modulus. And this is the first constant rate arithmetic garbling. If you compare with AIK previous results, their rate is proportional to the dimension of the LWE. Even when we look at a general circuit, even for garbling, just compare to garbling Boolean circuits, the only constant rate garbling we know would be these feasibility results assuming indistinguishability of fustigation. In fact, they would be completely different. They don't follow the gate-by-gate approach, can even achieve sub-constant rate. And similar results were achieved in the reusable garbling results using FHE and attribute-based encryption. However, the complexity is going to grow polynomially with the depth, and hence, to have the good rate, you basically think we can achieve good rate for depth-restricted circuits. Yes?
I realize I'm still a little confused between B and L.
P and L, okay.
B.
B and L. L is a log B in this case.
Oh, okay.
L is the bit length of the wire values. Any other question? Okay.
So wait, so the theorem is for arbitrary depth circuits, and that's what separates you from from BGG classes.
Exactly.
But you get constant rate, whereas for shallow circuits, right, you can get rate 0.
Yes, absolutely. Yeah, absolutely. Sub-constant rate using those more like advanced techniques. Another difference that separates us from the more advanced technique is that we have some potential for concrete efficiency. So for a specific setting, as I mentioned, the constant rate starts to hit when the integer length is comparable to the Palier key length. So we pick the setting that is most favorable to us, and we compare what's the size of a garbled multiplication gate using our method versus the size using converting to the Boolean solution. And here are the closed formulas, and with reasonable parameter setting that we can reduce the size from megabytes down to kilobytes. So it's roughly more than 600 times smaller than the Boolean solution. What about the computational comparison? That is much less clear because in the arithmetic world, we're doing lots of arithmetic computation, whereas in the Boolean world, we call AES, which is very fast. So roughly the trade-off is in our scheme, you do one multiplication mod n versus doing hundreds of AES calls in the Boolean solution. Okay, we're not claiming that we have concrete efficiency, but it does seem that there's something different here. Yeah?
In terms of parallelizability, are there big differences also?
It's also in NC1. It's gate by gate, and the processing for each of the gate can be parallelized. Okay, so we also can handle ZP computation, which were not handled before when we have the restriction.
So that's another difference from the BGG plus work, right? Where garbling takes depth as much as the circuit size.
Oh, right. Right. Absolutely right. It doesn't parallelize. Thank you. Oops. Okay. So we can handle ZP computation. The rate is worse. So the rate with using DCR is always better than the rate of using LWE. And here we will achieve a rate which is linear in the key length. Okay. And the important thing for us is that we do not kind of Booleanize, and we make black box use of the arithmetic operations. So finally, we define this mixed computation, which is any circuit that contain these three types of gates. You can use addition, multiplication, arithmetic gates, and we also want to have Boolean computation gate, which is any polynomial-sized circuits. And in between, in order to translate, there is a bit decomposition gate. Okay, so any circuit written composed of these three gates is the mixed model. So this does capture more realistic computation. For example, if you think about machine learning models, it often does some arithmetic computation followed by some non-arithmetic things such as comparison. What we can achieve is that we can directly have a method of garbling such circuits where the overhead for arithmetic gates is constant, overhead for the Boolean gates is lambda, which is Yale's Garble circuit, and the translation gate has kind of worse overhead, which is quadratic in the key length. Okay, so this is our result. What I will try to tell you a little bit next is how the general paradigm of garbling arithmetic circuits look like. This is from the AIK work. And the key element in this construction is what we call the key extension gadget. So this is all where the hard things come in. And then I'll tell you, we have an abstract way of looking at the key extension, which doesn't work straightforwardly, but I still think that it's very, very helpful to view it in an abstract way. Then I'll tell you what's the problem with the abstract framework, and you'll have to find a specific solution for each of the model we deal with. And I'll tell you particularly how we deal with it in the bounded integer computation. And if time allows, I will talk about the ZP computation, and I will definitely not talk about the mixed computation at all. Okay. So how do we imagine to gobble arithmetic circuit? Well, we're still thinking about gobbling it gate by gate, so we need some sort of a gadget for every addition and multiplication. And it turns out to be insufficient, and we need a new gadget called key extension. So the gadget for addition is extremely simple. Remember that the input labels are affine evaluations on the input value. So it is very natural that for each of the wire, we're going to think about the wire label to be the affine evaluation on the wire value, right? And this is indeed the case. Each of the wire label is going to be an affine evaluation of the wire value. The question is, the gobbling algorithm needs to specify those affine functions, right? And if I have a target affine function for the output of addition, where we have coefficient k0 and k1, then it's very easy to come up with the right affine functions for the input wires, right? Just make sure that k0 is still k0, and the constant part is going to be a secret share of k1. How do we evaluate? Add those labels together. You get the right output label. How do we simulate? Observe that one of the label is uniformly random because of the R. Hence, you can just simulate, if you are given with the output label, you can simulate the two input labels by choosing one randomly and compute the other one subjected to the correctness constraint. Okay? So this is going to be sort of like a universal thing that comes up a lot, how you can simulate. What about multiplication? It turns out to be also extremely simple. Well, what you need to do is to first have those two labels. Then you realize if I multiply them, it comes out with lots of cross terms. In particular, I will have r times x2, and I will have s times k0 times x1. So we add more labels in order to cancel out those cross terms, right? And we make sure that the constant part is going to be a secret share of the right constant in the output label. Okay? So therefore, I can set up all those coefficients to make sure that evaluation is computing this equation. And observe again that because all the constant terms are essentially a secret share of the right constant, of the output constant, simulation is again simple. Given the output label, I just sample all the three of them uniformly randomly, and reverse compute the last one, subject to the correctness constraint. Does this make sense?
So is there sort of an exponential in the multiplication depth of the circuit here?
Absolutely. So doesn't that just solve our problem? This is a fully black box construction of arithmetic gobbling. The problem is that, indeed, the dimension of the labels keeps growing, because if I started with dimension t, after addition, I stay at dimension t. After multiplication, my input label has to become 2t length. And in fact, there's another problem, which is some of the wire may have high fan out. And in that case, all the fan outs will have their own labels. So overall, the length of the label is going to grow exponentially with the depth multiplied with the fan out of the wire. So this limits this method to handle only logarithmic depth circuits. In fact, the same problem shows up when we have information theoretic gobbling for Boolean circuits. So the problem is shared. To solve the exponential growth, we want to somehow do key extension, or key shrinking if you prefer to view it the other way. What I want is, given a short label where A and B are dimension t, this gadget may publish some Garble table, is able to produce a long label with respect to the same wire value. Okay, so C and D may have arbitrarily much larger dimension than the input label. And the security is defined that given the output label, we should be able to simulate the short label and the Garble table. So as you can imagine, once I have such a key extension gadget, then we can solve the previous problem. Whenever the label becomes too long, we're going to insert those key extension gates to shrink the labels down to short ones, and then continue the lower computation. Simulation composes beautifully, where I can simulate. Given the label, I simulate the input labels, and I continue to call the simulation for the lower gadgets. So overall, the key lies in how do I design those key extension gadgets for some ring. Okay, so now I will tell you about the arithmetic, the abstract idea that we started with, though it doesn't work for an important reason. So let's imagine that if we just wanted to do key extension for Boolean computation, where the var value is just 0 or 1, then key extension is extremely simple. How? I can just publish 2 ciphertext, right? Because I know the short label is either x equals to 0, therefore equals to b, or x equals to 1, therefore equals to a plus b. And the output desired is either d or c plus d. Right? These are the only options. So hence, I can just publish a ciphertext for each case. This corresponds to x equals to 1. Oops, did I mess it up? Oh, yeah. This corresponds to x equals to 0. This corresponds to x equals to 1. Give those 2 ciphertexts. Whenever I get one of the key or one of the label, try to decrypt, right? And this, in fact, is essentially the idea behind the encrypted truth table. In fact, observe that we don't have a lot of requirement on those encryptions. I just need them to be one-time secure secret key, because the input keys are just random and never reused. They are wire keys, and they're just random for each of the gate. So, but what happens is that when we deal with arithmetic computation, where the wire value is exponentially, has exponential number of possibilities, then I can't do this enumeration. So it seems that we just need some more arithmetic property, right? Many people are nodding. This is indeed. We need this homomorphism property of the underlying encryption. Here, homomorphism means linear homomorphism on both key and the message. If I have this, then what should I do? Well, let's think that I just publish 2 ciphertext where A encrypts C and B encrypts D. Now, suppose for a second that the wire value is just public. The evaluator knows it. We're going to fix this problem later because that's exactly what we want to hide. But suppose it's public, then I can evaluate, I can key extend. All what I need to do is to use the homomorphism property to multiply the encryption of A, C with a constant x, add with encryption of B, D. What I will get is an encryption of the long label under the short label. Right? So then, evaluation is very simple. All what I need to do is to first apply the linear homomorphism using the public known wire value to obtain the ciphertext of the long label. And then given that we know what's a short label coming out of the evaluation of previous gates, just decrypt that ciphertext and that will reveal to me the long label. However, this abstract view ignores one important fact, which is I'm sort of pretending here that both the key space and the message space are exactly the same as my underlying ring, right? Because I get a short label, it's denoted as addition and multiplication, but it's addition and multiplication over R. And here, the addition and multiplication naturally happens inside the key space. So if those two things don't line up, it's useless, right? So this abstract view, we're pretending for now that the key space and message space are both the same as R. However, this is hardly true. And this will be the main problem we'll need to deal with. But so far, let's pretend we do have this property. Then this abstract idea is very nice, and we can easily show this is secure. How so? That ultimately, I want to show that the Garble table, which are those two ciphertexts, together with the short label, can be simulated by a simulator who knows about X and the long label. Right? How do I do that? Well, just apply the same idea we had before. Suppose I generated those ciphertexts. Instead of generating first ciphertext 1 and ciphertext 2, as in what the Garbling algorithm does, we're going to directly generate the output ciphertext, which is going to be an encryption of the long label that simulator knows under the short label, which it can just simulate itself because it has a fixed distribution. And then we're going to have ciphertext 1 generated and recompute the ciphertext 2 subject to the correctness constraint. So I claim that those two different ways of generating those ciphertexts are actually statistically close. Once I have done that, I need a property that the short label itself is going to hide the key A. So if I have that property, then observe that the ciphertext 1 is basically encrypted under a random and hidden key, and hence I can switch to random. And that's it. This gives me the entire simulation. But not you look like you're about to. What's your question?
I'm not sure what the question is.
So what is going on here?
So what you want to simulate is the encryption of L with S, right? This is the table.
I want to simulate ciphertext 1 and ciphertext 2. That's the table.
Okay, that's the
yeah.
table. Right.
I'm just saying that
The output is the encryption of the long label with the short label?
yeah. So I just reversed how they are sampled. We're going to first sample this one, and then sample this one, and then recompute this one.
Right.
Mm.
Right. And this thing says that somehow this property that the property that you just wrote down, which is ciphertext 1 is random conditioned on the other guys, conditioned on ciphertext CT, right?
Yeah.
That's enough to prove the
Exactly.
functionality because CT2 is a function of the other guys.
Yes. So what I crucially need is that the short label needs to hide the key A. In other words, in some sense, B needs to hide A. Okay, so that's the key property that the security depends on.
And if the reorganization, the homomorphism is still perfect, then it will be adaptively secured as a Garble.
Oh, I didn't think, yeah, I don't have a conclusion. I don't have something affirmative or non-affirmative. Quantum stage.
So also there was a public X in the previous thing. Was that like?
We're solving this on this slide. Clearly, I don't want X to be public, but the idea is I can make X okay to be public because I can just modify my underlying circuit every time before key extension. First, hide my actual wire value X using a random blinder. Then, the one-time padded wire value can now be public. After we key extend, we can always subtract away this random blinder. If you expand out all the labels, that's how it will look like, and it can be done. Okay, so let me now tell you a little bit about how do we solve the problem that first tell you indeed it's a problem. Key space is never the same as the message space, and how we can solve it depending on the specific computation. So let's see a concrete example of such a linear homomorphic encryption, in this case using Palier. So the most important thing to know about the Palier is it samples the modulus as the product of two larger primes, and it uses a modulus which is a power of this n. And the group structure is the following, that every element inside this group z n to the c plus 1 star can always be written in this format, meaning that the group is the product of two subgroups. One subgroup has generator G, another subgroup actually has generator 1 plus n. Okay? So every element can always be written as G to the x times 1 plus n to the y for the appropriate exponent x and y. And the G subgroup is actually hard. It has an unknown order, which depends on the factorization of n. The n plus 1 subgroup has a known order, exactly n to the c, and it is what we call the easy subgroup. What do we mean by G subgroup is hard? The assumption is that the random element in the G subgroup, G to the x, is indistinguishable from just a random element inside the entire group. Okay? In other words, if I have some G to the x, this sort of acts as a blinder for even the exponent in the easy subgroup. And what's easy about easy subgroup is that discrete logarithm inside this subgroup is actually really easy. Okay? And given 1 plus n to the y, there is an efficient algorithm that computes y. Okay? So this is really very nice for encryption, because you can imagine G to the x is the part that hides. At the decryption time, one cancels out whatever G to the x there is. You're left with what's inside the easy group, discrete logarithm. You will find out the encrypted value. And in some sense, it's almost like the encryption scheme using Palier is very similar to Algol using DDH, where you just do Algol using DDH in the hard subgroup, where we publish a bunch of G to the R in the sky, and with a secret key A, we get the hard subgroup blinder, which is G to the R times A. DCR will imply that this is going to be indistinguishable to G to the random. And we hide whatever message we want to encrypt inside the 1 plus n to the c, inside the 1 plus n subgroup. Now, clearly, this is very linearly homomorphic. If we do the desired homomorphic evaluation, what we're going to get is exactly this format. This corresponds to an encryption of AX plus D under the key, encryption of CX plus D under the key AX plus B. Okay, so everything lines up, except the fact that what's the key space and what's the message space? The message space is n to the c. The key space is this z p prime q prime, which we don't even know what's the size, right? Well, we can first get rid of the problem of unknown size by pretending that my key space is integer. If I know the key computed ax plus b computed over integer, obviously I can decrypt, right? And so that's still a problem, right? This integer is not the same as this one. And in some sense, when we're using Palier, what we're going to do is that we're going to evaluate we're going to treat the ring in the computation as z to the n to the c for some very large n to the c that is bigger than my integer bound b. Okay? So it's without loss generality to think about the entire computation is happening over z to the n to the c. So at least the message space kind of lines up. So the remaining problem is that the key space does not line up. What that means is I need to convert from ax plus b mod n to the c that I get from the arithmetic garbling, convert it into ax plus b over z. This turns out to be a pretty easy task when we know about the bound on the value of x, right? Because what if we can just make this n to the c large enough, so large to the extent that the mod n to the c doesn't never mod, therefore it just equals to ax plus b over z. And this is pretty easy to do once we set up the parameters right. A doesn't even need to be that big, and then here we're using a fact that the Palier's keys are pretty small comparing to n to the c. Make sure that we set the b to be significantly larger than a times x, which I can do because we have bound both on a and on x. This makes sure that the short key ax plus b indeed hides the key a. And that was, if you still remember that when we introduced the abstract idea, this is the key property that we need for simulation to work out, is that the short key ax plus b hides the key a. So in other words, that this works out pretty easily. Putting them all together, the evaluation is going to get ax plus b mod n to the c, and just treat it as over z. Compute the homomorphic evaluation and decrypt the output ciphertext using the integer key. And that will give us cx plus d mod n to the c. Okay. Does that make sense?
Can I try to understand this bounded values
Yeah.
assumption? So what? I mean, so if I somehow get a circuit and I have a certificate that says on every input, you know, the values and the wires are bounded by this b, then fine. You know, I can garble, no problem. But what happens if this I don't have such a certificate, and the input that I'm trying to garble has some large value in some wire, right? So correctness is not guaranteed, right? And potentially security is not guaranteed either, because, you know, if I'll try to decode, right? If decoding doesn't go through, somehow I detect an error, I know that the input was one thing.
Right. You're right.
So somehow you are assuming global boundedness. Somehow I have a
Yes.
certificate.
The boundedness is for the specific c and x, both of them.
Somehow I can't test it myself, right? Because that would involve potentially computing the circuit myself. But somehow I know.
Yeah, I mean, it is, I agree with you that this b-bounded assumption is a strong one.
I guess these are sort of like, I don't know, these like whatever neural networks or whatever, you compute the kind of Lipschitz constants, and you can try to get a global bound on how big numbers grow, perhaps.
Yeah, it's not very clear that what realistic computation is only doing integer computation and still having a global bound without ever doing truncation or doing something. And I definitely think that the most realistic computation model is the mixed computation, which I unfortunately don't have time to talk about. I think nevertheless that this is perhaps a component inside a mixed computation, which we could do is that arithmetic gate only has constant rate. But then we need more ideas in making the bit decomposition more efficient, and I will talk a little bit at the open problem section, yeah. So quickly to go through that, if you want to have an instantiate from LWE, it's extremely simple because LWE encryption looks like using the key A multiplied with a public matrix and encrypt the message with a large scalar that separates the message from the noise. And this construction is also very arithmetic, linear homomorphic. And we see the problem again. Basically, the message space is going to be for some ZP, but the LWE modulus is bigger. And we can solve this problem by, again, pretending that the key space is over Z, and just use the previous method to leverage the boundedness of the wire values to obtain AX plus B over Z. So I don't have much time to talk about the ZP computation. Let me just quickly give you some idea about what would go wrong. So once we go to the ZP computation, what goes wrong is exactly how do we deal with AX plus B, that we obtained AX plus B mod P. Now this P is exactly the P of the computation modulus, but in order to decrypt, I want AX plus B over Z, which I don't have. And unlike the bounded computation case, where X is much smaller than the modulus, here X is as big as P, right? And has definitely information has lost. There's seemingly no way that I can go from AX plus B mod P to AX plus B over Z. And nevertheless, we figured out a way to do so. And that explains why the scheme is less efficient than the bounded integer version. What it involves is that we have to pick A and B's according to very special distribution, where A, first of all, is going to be Boolean, and B is going to be from a range, either is from 0 to P minus 2, or P over 2, if A is 1, or P over 2 to P if A is 0. So pictorially, let's think about two cases, where the first case is X itself is smaller than P over 2, then either A is 0, and therefore the short label AX plus B mod P is exactly ranging from P over 2 to P. So this is the range where the short label is going to come from, some random value in this range. In the case where A equals to 1, so then we do get X plus B mod P. And B in this case is chosen to be from 0 to P minus 2. So therefore, this is some range starting from X, the value of X. And we can plot the other case where X is bigger than P over 2. If A equals to 0, then it's still from P over 2 to P. If A equals to 1, then it will actually, X plus B is going to become possibly larger than P. And in that case, it's going to wrap around. So what you're actually going to see is the value being here. So observe that the only time that AX plus B mod P does not equal to AX plus B over Z is when this happens, right? And when does this happen? I actually know when does this happen, because X is a public value when we do key extension. We know it. And if I observe X is bigger than P over 2, and the short label is actually smaller than P over 2, this thing, then I know that mod P has taken effect. So all what I need to do to recover the right value is to just plus P in that case. In all the other cases, AX plus B mod P equals to AX plus Z. So this is our idea of recovering the integer value. There's lots of problems I won't tell you about. The problem is, what about security, right? Does like AX plus B still hide A? The fact is that it does sometimes, because those ranges always have some overlap. And then we have to solve more problems, including the case that A doesn't have a lot of entropy. It's like a single bit. In fact, it's only hidden with probability half. So I need to somehow aggregate them. And I also need to deal with the case where, the hiding property security only happens for some range of x. Okay. Without going too much into the details, let me skip this part and just to the open problem part. Okay, so I think this hints at a couple of very interesting open problems. One is that what kind of computation can we get constant rate gobbling? That we showed for this bounded integer computation. It's very nice, but it's, as we have all realized, that maybe it's a little bit hard to imagine a realistic computation that does have this boundedness. But what about the constant rate for other models of computation? For ZP computation, and what about even just for Boolean computation? Why cannot we have constant rate? In fact, that theoretically, we do have constant rate using strong primitives like IO, FHE, or ABE, but can we do it in a perhaps closer to practice way? And the second question is, I do think that the mixed computation model is more realistic. However, currently, in terms of efficiency, the bit decomposition is quadratic in the key length. It's not very efficient. But can we think about improving that efficiency generically? Or can we just target on a few important Boolean computation that people use, such as truncation, threshold, and comparison? Can we directly design gadgets for those computations and compose with the arithmetic gobbling? And that perhaps will give me more efficient gobbling for some realistic computation we care about, such as machine learning models. Of course, there's the question that why only Palier and LWE can we have other assumptions? And that's it. And finally, I want to say thank you, Ran. And I was your postdoc 10 years ago, where 10 is not a number I want to remember. But still, an anecdote about Ran is that I remember I met him with Raphael together in Boston. We were sitting outside some coffee shop and talking about research. And later on, that quick meeting actually immediately turned into a paper that when I came to Boston, I started working with Ran. And during the submission time, I went to Ran's place. Ran is always very inviting. He said, why don't you come? So I went, and I was like typing and typing and typing. And Ran cooked some really amazing pasta for me for lunch, and I could barely eat. I don't know if you still remember. It was quite spicy, but really, my mind was not about eating. and then afterwards, I don't know if it's right on that day or afterward, like a few days later, you told me that, you know, we can work hard, but we can also enjoy life. And I think that was like a very nice introduction of Ran to me, is that he's a really, really nice blend of both work and life. It gives really good scientific advice, but also life advice. And when I think about Ran, I always think about this very, very big smile, and there's a sense of warmth, and there's a sense of ease, and there's a sense about colorful life, like your pants. So thank you very much. So the definition is simulation-based, so it's enough to talk about a pair of C and X.
But sort of the simulation works when X is...
the simulation works
X
if...
has this property that
Yes, yes. It leads to a computation where every var value is bounded by b.
So in other words, that fact is not hidden by the.
Right. Whether or not the if so in right this sort of.
It would be nice to have at least a version where if x does not lead to b boundedness, then it's still secure somehow. Maybe correctness no longer hold, but or maybe the only information is.
Here, so it would have to be like, well, actually correctness holds if it's equivalent to some other input that would lead to b-bounded wires or something weird like that.
Great. So
Yep.
let's thank you again.
Is going to tell us about a really cool result on locally covert learning.
Thanks everyone. Oh, it's kind of echoey. Thanks for the introduction. This is joint work with Rita Jawala, who's a student of Dakshita at UIUC. She did her summer internship at Entity Research. So if you want to do an internship, come talk to me, I guess. Right, so yeah, I mean, I guess this talk is kind of a learning theory talk, and I know we're mostly cryptographers here, I think. So I'll do a little bit of a background on learning theory before we jump into the result statements. So the basic setup in learning theory is that you have a learner. So here it's this dashing young scientist who is interacting with a function in a sort of black box way. And the goal is to then compute a representation, like an explicit, something that you can write down that approximates this function. So there's a ton of variations in this model. So I'll just talk about like the specifics of what I'm going to focus on in this talk and not get into every single way that you can change things. But in this talk, when I say that a class of functions is learnable, first of all, in terms of efficiency, I want to say that there's like an accuracy parameter and a confidence parameter, like usual. It's kind of weird that I can't see the screen here. But anyways, the learner runs in time that's like polynomial in the input length and the inverse of the accuracy parameter and the log of the inverse of like this confidence parameter. So in particular, this means that if you set the accuracy to be any inverse polynomial or the confidence to be exponentially, or the error probability, I mean, to be exponentially small, you can still have the learner run in polynomial time. So this is, I think, kind of the gold standard for efficiency. And we'll also focus on a type of learning that's called weakly agnostic, or if you don't want to read the mathy stuff, you can think of this as learning with worst case noise. So if you have, if your function is close to being representable by some nice class of functions, so like, I don't know, say H's decision trees or something, then the learning algorithm can output a hypothesis or that is almost as good as the best nice function. So here I'm allowing like a constant factor blow up compared to the original distance plus some additive slack that you can set to be arbitrarily small. And of course, there's some allowable error probability. The little h, yeah, it does not to be. That'll also appear on this slide. I'll talk about that more. So one more thing before that is that in this talk we're only going to talk about learning with respect to the uniform distribution, which means that we say that a hypothesis is good if on most of the inputs, just counting every possible input equally, it agrees with the true function. So sometimes in learning theory you talk about arbitrary distributions which can like focus on a very sparse fraction of the input space. But that's too hard for theorists, so mostly. So we focus on the uniform distribution. It's instead of O of epsilon, you just have epsilon. Yeah. And that is much more difficult, too difficult for us, for me, today. Maybe in the future I'll focus on that. What? I'm talking for upper bounds, it's difficult, yeah. And so what Ron, I think, was asking was about the properness of the learning model. So here we're allowing the learner to output circuits, even though it might be focusing on functions that are representable by, say, like a decision tree or something. Okay, any questions so far? I know this is just like a, yeah, in the back? Oh, sure. Okay, yeah, you can weak into that, but I think in this talk everything is going to be log of 1 over delta. I didn't check super carefully, but I think it's basically just there's just some turn-off bounds, and I think you can get log of 1 over delta. Okay. Yeah. So I think like most of what I'm going to present in terms of what's known and not known, is not going to change if I make that relaxation, because mostly I'll be talking about upper bounds. Yeah, I'm going to be talking about Boolean functions. Any other questions so far on a model? Okay. So the next part of the last part of the learning model just has to do with what exactly I mean by the learner having access to, or black box access to a function. In particular, there's two natural settings. One, which we'll call passive learning, but in learning theory literature, it's called like learning from random examples, is where the learner gets just input and output pairs. It doesn't get to choose the input, it just, they're sampled, in this case, from the uniform distribution. And it can get as many of those as it wants. And another more powerful model is where the learner is allowed to make whatever queries it wants to this unknown function. It always, well, so, yes, but yeah, I mean, I guess you can play that. So I talked about where f might only be like close to your class, so the other, some small fraction of points could be arbitrary. So I have a weird shape on the next slide, but I wanted to, were there any questions? So there's a lot of stuff that you can learn in the model of Describe so far actively, and so like, I guess I'll explain what all the things in this slide are, starting from the, so if you have a function that just depends on logarithmically many variables, that's like the kind of simplest function that we know how to compute with membership with queries, but not from random examples. And you can generalize this to decision trees, and you can even go as high as like Fourier concentrated functions. And also, if you either make assume a conjecture, or if you slightly change the learning model, you can also do DNFs or CNFs, so they're kind of the same thing. But there's really not so much that we can do passively. I will also mention that I'm talking about polynomial time algorithms, right? And if you allow just quasi-polynomial times, you can do the stuff on the left. You can even learn AC0 passively. So it's just kind of a fine-grained separation. But on the right-hand side, if we're talking about agnostically learning parities or Fourier concentrated functions, then we don't know how to do it in quasi-polynomial time. And of course, if you go beyond AC0, let's say even to TC0, then everything is hard. There's basically no learning up there. Yeah? Oh, yeah, it's, I think, yeah, so for DNFs, I don't think we know how to learn them agnostically. Yeah, but under the assumption that they are actually Fourier concentrated, then you can, weakly agnostically, and yeah, let me not get into it more than that. Okay, so that's like all the kind of learning background, the standard learning background. And as cryptographers, I think we're always asking the question, like, where's an adversary? Like, give me somebody to fight. So, so yeah, the study of adversarial learning is by now a burgeoning field. I think Vinod has a great survey talk. I forget where exactly. Okay, but if you search for Vinod and adversarial machine learning, I think you'll find something. But today, I'm just going to talk about two particular sort of security properties that you might care about in learning. So the first one is called covert learning. This term is due to Ron, and it involves an active learner where somebody else is sort of watching all the queries they make, and they're trying to get something out of seeing you make these queries and the responses. and for whatever reason you don't want to share with this eavesdropper. And another property, which I'll talk about a little bit less, is verifiable learning. We're here not so much worried about leaking information to third parties. You're worried about third parties trying to fool you, or so maybe yeah, I'll talk about it a little bit more later. So. Yeah, well, I guess this doesn't explain in super much detail, but yeah, you get to see the queries and the replies. It's sort of the whole transcript of the interaction with the oracle, but you don't get to see the private randomness. So here's a picture. I don't know, I just drew arrows in both directions to indicate that the information kind of goes back and forth between the learner and the whatever oracle is implementing the function. And so I guess if you want to give a nice cryptographic definition, you can use the ideal real paradigm and say, you know, whatever the adversary sees on the left side, you can simulate given only random examples. The simulator here is passive. Actually, in all of the constructions for covert learning that I know of, it actually involves a learner making just random or pseudo-random queries to the oracle. So in this case, the simulator is really passive. It just like forwards the queries, you know, whatever random examples it gets to the adversary. And sometimes it's useful to have this stronger property that the queries look random. Oh, just in the constructions that. Oh, I mean in covert learning. So technically, there's a small difference between the queries being simulatable by random examples and actually being random examples. But yeah, in Goldrake 11, at least the version that we know, it's yeah, you're right. The queries are not random. And I'll talk about that more later. Good. So we can also consider what I call locally covert learning, where you have more than one implementation of this function. And the learner can send some queries to one implementation, other queries to another implementation. So the adversary gets to look at either one of these transcripts. And it's, again, in either case, it's supposed to not learn anything more than it could learn from random examples. Just that the adversary can only look at one. So from a learning perspective, there's no point to having extra oracle. Yeah, exactly. Yeah. Mm-hmm. Yeah, I mean, aren't those the same? Aren't those the? Or like you said, the simulation definition isn't that equivalent to like learn no more than? Okay.
No. Okay, that's not what I meant to say. I guess that's what comes out.
Yeah. It's just.
But you know, like you could say, you know, if the passive learner, the purely passive learner takes 100 queries, then you know the person who eavesdrops cannot do.
Oh, I see. I see. You're saying there's not even like a polynomial blow up in the number of queries the simulator takes. Yeah. So in fact, I think all the constructions that we know achieve this stronger notion.
And also just to check, sorry, I might have missed this slide we discussed, but in the passive learner, is it like IID? There is like some switch.
Yeah, it's IID.
So how important is that? I mean, there are the two aspects.
It's very important. Like you can think of active learning as just getting correlated queries where you get to choose the correlation.
But I guess the question is, I mean, there are the two aspects. One is like I choose input 2 based on output 1. But there is another model maybe that, you know, my queries will be x plus 1 and like no.
Yeah, so actually like like the active learning that we know, you can do all non-adaptively. Like for example, like in Goldrake 11.
So
Well, I mean, there are stronger notions of learning that go all the way to totally arbitrary distributions, and just require. But that there's very limit.
But the input x2 is distributed the same as x1, as the same as x3, x4. This is critical. I mean, I'm not arguing uniform versus non-uniform. It's just the fact that identical.
I mean, this is like the sort of weakest form of or like the weakest form of access to a function that you can imagine. So it's sort of natural to study. Like you go out on the street and you look at a person and you sort of classify them, and then you learn. I don't know, but yeah, I mean, you could ask for. I think people have studied models like in between passive and or like full membership queries, but they're. Yeah.
Maybe saying that you want to simulate by passive, that like that from the attack's point of view, it's as good as just getting passive queries. Maybe it's too strong. Maybe it's just good enough to say, the observer cannot learn the function, but the actual guy can.
Right. You could have with like a search problem, I guess. But we'll see. Even with a strong notion, we can get pretty far.
Because you want to combine it with something that's not passively learnable.
Yeah. Right, yeah. And that's sort of one reason, I guess, to sort of separate the simulation by passive versus the hardness of passive is that it'll let us get some information theoretic stuff, which at least is good for writing papers, if nothing else, in the first part. Okay, so I want to try to motivate covert learning, and I'll do it like 3 times. So I hope I convince you at least once. So one sort of setting is that you're just trying to delegate, or actually 2 settings. You're trying to delegate scientific discovery. So you want to learn some function, and I'll just suppose that this is a function where it would be really useful to have membership queries, but you have a lot of random examples instead. So let's say, like for example, I really like this example. You're trying to learn for some species the map from the DNA to the feature, the sort of traits that this organism expresses. So you can sequence DNA pretty cheaply these days. So you just take a random thing and just poke it. I don't know how it works with the needle and put the needle in the machine. But if you want to actually make queries, you have to synthesizing DNA is much more difficult. You can do some breeding, but it sounds like a huge pain. So you want to take this. You want to let someone else take care of all of this stuff. But I don't know, you're a paranoid cryptographer, academic or something. So maybe the specialist that you outsource to is going to do the experiments and take the resulting data and sell it to a competitor, your arch nemesis. So one thing that you can do with covert learning is try to make the data that any one lab sees have like no resale value, or they'll only be as good as random examples, which everybody has access to anyways. As long as you keep your randomness private, because it's cryptography.
I see. So you're saying this is incentive to, like you want my lab when it writes a paper to publish the data,
Mm-hmm.
like to publish the queries and the answers. And you say, okay, I'll do it. It's useless to you.
Yeah.
But it's also not reproducible. They won't be, if you publish the data, you won't be able to run the experiment without your private data.
Yeah. Well, yeah, but maybe you, I don't know, like maybe you switch to a model where you like commit to your randomness and do a proof or something, and just have some other like more modern verifiability of science.
The problem is you want to prevent being scooped, right? Once you're publishing in a journal, it's okay to add your randomness. Just clarifying the incentive model here.
Well, we're not biologists, right? So I've been told this is a friendly room, so very not serious. Nobody's scooping anybody. Okay, so let's say again that you want to delegate learning some function, but now you're worried about something different. You're worried that that you'll get bad results, that maybe the person you outsource the learning to doesn't give you a circuit or that is as good as it could have been. So actually covert learning, at least some strong versions of covert learning, give a way to get some verifiability, and it's a little bit similar to how in classical delegation you can go from privacy to verifiability. So you sort of you're going to micromanage the person you're delegating to a little bit. You're going to like tell them exactly what queries you want them to make, and it's going to be according to to a covert learning algorithm. But you're also going to mix in some random queries that you already know the answers to. And you can do this because random examples are cheap and abundant. So because all the other queries just look uniformly random, if the prover answers correctly on the queries you hid, then most of the other queries have to be answered correctly too. And most learning algorithms are kind of robust. Like if a few queries are messed up, it's not too bad for the output. So this gives you some way of checking a learner. No, here you really do not want the simulation definition. You want the queries to actually look, because you want the queries to look random as opposed to being simulated from random examples. Sorry?
Says whatever you can learn by making these queries, you can simulate from
No, like you can, but if you have the private randomness that you use to generate the queries, then you can learn more than without, that's, so.
So it's private because you want to have a positive result. It's private coins to generate the queries. You can learn something, but the transcript itself doesn't teach you.
Yeah, I think that's right. I'm saying that if you have a covert learning algorithm for some class of functions, then you can also get some kind of verifiability. Like you can, even if you have an untrusted oracle now for this function, you can still learn given random examples that you do trust.
I'm not sure I understand the scenario. Like you get some model from the learner.
So you're outsourcing the evaluation of the query, and maybe this person you outsource to, they don't actually want to do the work of making the queries. Does that make sense?
Right. But can you always test, even if you don't have you can get random queries yourself afterwards. You can always test the model you learn and see if it's correct.
Right, but you don't, okay, that's a great point. And I do have so here, remember we're in this agnostic, you don't know how good is optimal.
I see.
So
I see. So you know you got a good model, but you're not sure you could have gotten a better one.
yeah. Okay, so and finally one last scenario, which again I think was discussed in Ron and Ari's paper, is that suppose that you're now a business and you're trying to sell AI as a service, like ChatGPT or something. And when you make these things for the first time, it takes a ton of data. And maybe part of the reason is because it's just easier to collect large amounts of random examples than it is to collect large numbers of humans to consistently and label stuff. But now once you have this thing trained, you're allowing people to run queries. And maybe your competitors are going to use queries to learn the same model but cheaper, or a similar model. And this is like I should have had more citations. People have talked about this, thought about this. And one of the proposed defenses is that you just look for people making suspicious looking queries and you block them. But I guess covert learning kind of says that this strategy isn't going to work very well because the queries might just look like random queries. And I don't know, maybe random queries look suspicious, but in this world we'll say that they don't. So yeah, I hope you are convinced that covert learning is worth studying. So thanks again, Ron, for studying this or initiating the study of this. And Ari, sorry, but it's his birthday, so.
As far as we know.
Yeah.
My birthday is sooner than his.
Oh, really? Okay, sorry.
It's a
Okay, so now if you want to study like how much you can actually learn covertly, like clearly it's somewhere in between passive and active, because I mean you are just still learning with active queries, and if you could learn with passive queries, then it would just sort of trivially look like yeah, you wouldn't, I don't know. So here's what was in this previous work of Ari and Ron. Ron and Ari, I don't know. So they showed, and correct me if I tried very hard to be accurate. So they showed that you can, I guess, yeah, they showed that you can learn covertly decision trees and parities, assuming that the hardness of LPN. And actually, I think if you assume Mansur's conjecture, I think their thing should also apply to DNFs, because they're Fourier concentrated and like low degree. And in this work, we show that if you talk about local covertness, you can do more. You can get like basically every class of functions that I know to be actively learnable, although I probably don't know every active learning result. So it's a two, yeah, or more, yeah. And so for a while, I didn't really know what there was beyond parities, like a natural class that is in this light green zone. But I guess there's like this notion of a parity decision tree, which people have studied before, where if at each node you, instead of branching on a variable, you branch on a linear function. I don't know, it seems natural anyways, and this sort of falls outside of what I think was covered by the previous result.
And you don't have assumptions, or?
No assumptions, yeah, it's a perfectly covert.
So you also include the light blue area without assumptions?
Yes, but in the two or more server model.
So are you really going to learn 2 versus 1, or n versus 1, or n versus n minus 1? In the sense of like how many servers?
We just need 2, but you can
I can look at 1.
you can also strengthen the security to be k minus 1 out of k covert.
Or weaken it to be 1 out of k.
So that I don't know how to do better than k minus 1 out of k. Actually, it's a good open question. Like, so, because I'll talk about it later. I mean, yeah.
I would secret share my input and let these guys kind of.
But you need the learning algorithm to kind of, like, you can't do MPs. You can't like run this like organism like under an MPC, or is that what you're thinking? Or,
Yeah.
but like,
Developers are only allowed to actually answer learning queries.
yeah, they only have black box access to the function. How like some, how
As long as the secret shares come from the same world as the inputs to the function, right? Okay, then I can take it up.
I don't know how you like run E. coli homomorphically or something. Yeah?
Does the adversary get to switch between servers?
No, I'm just assuming the adversary is like fixed. Like in the beginning of the protocol, the adversary latches onto one.
So maybe you said this, but for the tail,
Yeah, the locally covert. Sorry.
covert, are those known not to be covertly?
Oh no, that's not known. And yeah, maybe you can improve the computationally single servo covert results.
I see. So for all we know, all of this could be included in the tail.
Yeah.
And sorry, not separation from passive to outside provable. So like parity is provably not passively large, not provable.
Oh, no, I don't think anything is provable. Because it's like it's a computational, like saying that something is not passive, like everything is statistically learnable passively, and to say that you can't do it efficiently, that requires some assumption. Yeah, and so I think, yeah, but there's, I guess Blum has offered a reward if you figure out how to even learn log n juntas passively, and we don't even know how to do it for like slightly super constant.
So all we know
Yeah, sure. For all we know, P equals NP and beyond. I think so. I think if P equals NP, you can probably learn like all polynomial size circuits efficiently.
But you're doing locally, so the main difference is you're doing locally Covert and they do Covert, right?
And information theoretic versus computational as well.
Is it inherent, or maybe that's Emma's question, it's not inherent that Covert has to be computational function?
No, as far as we know, like all of this could, like the only part of this that we have good reason to think does not collapse is active versus passive. But as far as we know, like everything actively learnable could be learnable computationally covertly.
But in particular, if you have Covert thing, information theoretic Covert stuff, it doesn't collapse to passive, for example, right?
No, it doesn't. Yeah. Oh yeah, and also, so there was another like earlier work by ICOS 2019 that showed that also considered the local covertness notion, and they showed that just like small juntas, you can learn information theoretically with a 1 out of 2 covertness. And so we do a lot better than that, I think, and, or a lot more. I don't know. So, anyways, that's kind of the overview of the results. The technique is all about Goldreich-Levin. So we all like know Goldreich-Levin, but I think some of you only think that you know Goldreich-Levin. So there's many ways of seeing Goldreich-Levin. So I think learning theorists use Goldreich-Levin almost as much or more than cryptographers. So the learning version, or like the Fourier analysis version, is that if you have oracle access to a function, you can find all of the parity functions that are significantly correlated with that function. And just to like, in case this doesn't look like the Goldreich-Levin that you know from your crypto class, I'll just quickly try to explain why they're the same. So the crypto version is that if you have any one-way function, the sort of inner product with a random string is a hardcore bit, mod 2. So I guess I'll just walk through this. So sort of inner product, mod 2, if you fix one of the inputs, that's a parity function. So at least so far we're starting to see the same things. And if this function is not hardcore, that means there's an adversary that can predict the parity. So like for a random R, it will, with like better than half probability, predict the inner product of R with X. And then, so this inner product of X with stuff is one of the parity functions that's well correlated with this adversary. So when you use the adversary, the hardcore bit adversary, as the oracle for the Goldreich-Levin learner, then you'll get a list of parity functions, and one of them will just be this input X that was supposed to be hidden. Okay, so that's, oh, sorry, I got confused about which slide I was on. But yeah, anyways, those are kind of the same theorem. But I think the less known question is like what the original Goldreich-Levin algorithm actually is. So I think a lot of times when we learn the Goldreich-Levin algorithm in crypto classes, actually like in every set of crypto notes I've ever seen, the algorithm that is taught is actually due to Rakoff. And like just as a quick test, if you have ever seen this thing of taking all subset sums of logarithmically many vectors, that's Rakoff's version. And so an important feature of this is actually really important that like de-randomization is kind of central to this. Like you want to guess like 1 bit per vector or something. So the queries that this version of the algorithm makes are very far from statistically uniform. They just don't have very much entropy, like a sub-constant entropy rate. And in contrast, the original Goldreich-Levin algorithm, which is actually very different. It does use Fourier analysis, which is probably why it's not taught, because as you'll see, teaching Fourier analysis is really a pain. But learning theorists still use this original version a lot, and like it's in Ryan O'Donnell's book. And so what we kind of show in this work is that if you look at the original algorithm, it actually is basically already 1 out of 2 covert. You can just take the queries that the original algorithm makes and split them across 2 servers such that each server individually receives uniformly random queries. And we show like how to modify this also so that you can get stronger k-1 out of k covertness, but it's like kind of straightforward. I don't know, the Fourier analysis is like pretty elementary. I'll bet you could figure it out if I sort of sketch it to you. All right, so locally covert Goldreich-Levin algorithms. Oh, Vinod looks like he has a question.
So we do this complication of non-IID queries. It comes in because you want to handle oracles that agree with parity on the half plus epsilon fraction, right? If you're okay with only handling oracles that are 3/4 plus epsilon.
Sure. Yeah. Then you'd be good. No, I think I agree with Vinod that if you have a high agreement with a parity function, then you should be able to find it.
Right. So the distinction is between unique decoding and misdecoding, right? The 3/4.
Oh.
So are you doing a pair comparison?
Well,
the right, does it actually do like half plus?
Yeah, it does. So the previous work on covert learning also sort of adapted Goldreich-Levin. So they gave it, but it didn't like get the full functionality of Goldreich-Levin. Instead of getting all parity functions, it would just get the parity functions that depended on a small number of variables. But it was single server. So it's just, here's a sort of diagram of what the previous Goldreich-Levin did. And I like saying pseudo-uniform better than pseudo-random because it seems more accurate, but I don't think anybody else does that. Yeah, so I guess our kind of main technical lemma, even though it's not that technical, is that there is a kind of a perfectly k-1 out of k covert algorithm for any constant k that does Goldreich-Levin learning. So it gets all the parity functions, and that's what lets it generalize beyond the sort of low degree stuff to like parity decision trees and beyond.
Just kind of coming back to the question, is it, to me it seems like it should almost tautologically be true, but assume I have something which is covertly learnable, but not passively learnable, right? Can we argue that boundary functions exist?
Oh, yes, I think so. In the single server setting, yeah. Like, because the problem of like going from the queries to the randomness should be hard. So that's like for your specific protocol, or is that a general thing?
I mean, it's been a little while, but
Okay, yeah, I can talk about it with you offline later. Yeah. Okay, so I'm going to try to teach you the bare minimum Fourier analysis that I need to kind of give some taste of our proof. So yeah, Fourier analysis is all about like the correlations of Boolean functions with parity functions. So in this talk, I guess I'll denote parity functions by the letter gamma. I don't know, Ryan O'Donnell did it first, so if you don't like it, blame him. And so these correlations, what I mean by correlation is like it's some number between -1 and 1. If the parity is like always the same as a function, and the correlation is 1, and if it's never the same, it's -1, and in between it kind of is what you'd expect. And we call the correlation squared the weight of a given parity function, because for any Boolean function, the sum of the weights of the parities is equal to 1. And that has a nice implication that there's not too many heavy parity functions. Like, because just all of these, this is a sum of non-negative numbers that's equal to 1, so there can't be too many big numbers. And so I guess the main lemma in the Fourier analytic proof of the Fourier analytic Goldrake-Levin algorithm is that you can estimate the weight of not just one parity, but like the sum of the weights of many parities all at once by making membership queries. So, I guess in the original proof, you can kind of bucket different parity functions by a prefix. So, like you say the parity is going to include some of these like first k variables and not include the other ones. And then you consider all parity functions that look like that, and you can efficiently estimate to whatever accuracy you want the sum of the weights of all of those parities. Oh yeah, here there's some notation. Yeah, so in fact, when we look at this subroutine, you can do it 1 out of 2 covertly, and that's like all you need to do the whole Goldrake-Levin thing locally covertly. And yeah, I'll prove this a little bit later, but first I want to just convince you that this is all you need to do Goldrake-Levin learning. So the basic idea is that you just compute all of the parities bit by bit. So the idea is that sometimes just looking at the prefix of a parity, you can already tell that there's no heavy parities that have that prefix. So that said, what you can do is you start with some prefix. At every step, you just throw away what you know is not going to work. And by the observation earlier about there being not too many heavy things, you know that you're not going to have to keep too much stuff around. At any point, you'll have 1 over epsilon prefixes. And then you just refine in the natural way. For every prefix, you can think, what if you add 0? What if you add 1? That doubles the number of prefixes, and you repeat. That's all. So that's like the original proof of the Goldrake-Levin algorithm. I think like the actual original paper is really hard to read, but as far as I can tell, that's what they do. And I think O'Donnell's book kind of has a slightly cleaned up, easier to read proof that looks similar. So, okay, any questions? Right. So I'll no matter what prefix you're looking at, the queries still just look uniformly random to either oracle. Okay, so yeah, all I need to kind of prove to you to finish everything is how to weigh these prefixes. And I'm not going to actually prove everything from the bare bones, but if you've like seen some Fourier analysis before, you should get a rough idea. So. Actually, I think it's more natural to just notationally and conceptually to think not of these like fixed prefixes, but to think of affine spaces of parity functions, whatever. So in particular, when you consider the set of all strings that share a particular prefix, that's one example of an affine subspace of all like the n-bit strings. Cool. And yeah, this more general thing we can also do covertly. Okay, so this is the revised lemma, and I mean, oh yeah, I guess I'm going to show you even less than I thought of how to prove this. But basically, you can, if you know a little bit of analysis, you can derive some sort of formula for the sum of squares of Fourier coefficients in an affine subspace. And so it relates this sum to an expectation. And so here you're sampling a pair of inputs, x1 and x2, that are correlated in some way that's related to the original, whatever, to the affine subspace that you're trying to weigh. So their sum is equal to something in the orthogonal complement of the vector space that the affine subspace is parallel to. Yeah, but the point is, I guess, that one is that this expectation can be sampled directly. You can, as a learner, you can sample a bunch of pairs x1 and x2, query the pairs of oracles, and then get a sample and then average. And you should be good by turnoff because all of this stuff is bounded and IID, et cetera. And these pairs x1 are sort of, each xi is individually uniformly random because it's just an additive secret sharing. Gamma star is a constant. So that's like your affine subspace is shifted from 0 by some constant, or like, and gamma star is what? So gamma star is a parity function, and x1 plus x2 is a string, so you take the parity of the.
So I can compute that given gamma star of x1 and gamma star of x2.
Yeah. Sorry, can you say that?
Gamma star is a parity function.
Mm-hmm.
So effectively you're taking a product of gamma star.
Yeah, I'm thinking of the output of the parities as being plus or minus 1 valued, if that answers your question at all. I'm not sure.
Is it the same as minus 1 raised to the power of the product?
Yeah.
Oh, so you're taking a product because it happens to plus minus 1.
Yeah. Right.
But the gamma star is something the learner knows, right? He knows the subspace A. It's only the F that.
Yeah, the learner knows what subspace it's trying to weigh.
So he just queries F on x1 and x2.
Yeah. This local computation, yes. Yeah, so that's I think the 1 out of 2 covertness is pretty clear. And in my remaining 7 minutes, I'll just talk a little bit about the generalization to, actually maybe just in 2 minutes I'll talk about this. Or sort of, if you want to generalize beyond 1 out of 2 to k minus 1 out of k, there's a natural generalization of this formula, as you might expect. If you want to look at kth power, so yeah, the thing is you have kth powers of your Fourier coefficients instead of squares, and you have an expectation over additive, a k-wise additive secret sharing of some vector. It does introduce a couple of issues that we're focusing on these sums of kth powers instead of squares, but it's not too bad as long as k is constant. So we'll call this a sum of kth powers, the k weight of A, and I'll just always assume that k is even, because you can always make something less. You can go from k, 3 out of 4 to 2 out of 3, for example. So yeah, we just use basically the same strategy that I outlined earlier. So let's see what happens. So again, you do this thing where you're trying to throw away prefixes that are too light. But now, in order, you only know that a prefix cannot be extended to a heavy parity if its k weight is much smaller, like epsilon to the k over 2. And as a result, you have to keep a lot more prefixes around. You can still bound the number that you need just by using the fact that the k weight is lower than the 2 weight, because Fourier coefficients are between minus 1 and 1, and so you take the kth power, they get smaller. Yeah, it's the same strategy. It does have this annoying thing that the running time is exponential in 1 over epsilon to the k, which is why I want to fix k to be constant. But yeah, that's all as far as techniques. Any questions about that? Okay. So yeah, I think there is a lot of possible future work, like low-hanging fruit that I should actually be ashamed of not having thought about any of these questions more. So maybe that'll entice you. So the first question is, of course, can you close the gap between what's locally covert? I mean, there's a lot of gaps here that we don't know if they're essential. So like, can you use this Fourier analytic thing in the computational setting to get better single server covert algorithms? Is there any gap? Like, so I kind of suspect that you can. I mean, never bet against cryptography being able to do stuff. But I'm like less convinced that you can learn everything covertly that you can actively. Like, somehow I feel like you should be able to contrive some weird function family that you can learn with queries, but I don't know, maybe. Like, I just don't, it seems, no, I'll bet against information theoretic crypto, but I'll never bet against computational crypto. Oops, sorry. Yeah, and I guess I focused on this one very specific learning model just because it's what the previous work on covert learning and verifiable learning focused on, but you can also look at other learning models and ask basically the same questions. And yeah, finally, I only did k-1 out of k covert learning, but and it did seem like there was some technical reason that it wasn't immediately clear how to take advantage of only needing security against t different oracles.
Your best hope is just to get that mean reach. That's the only thing you're missing.
What do you mean?
For that question Q4.
Well, I mean, so you could hope to, you could reduce the dependence on k. Like maybe you can get like 1 out of k covert. Like even for the classes you can already do, you can hope to do them more efficiently when you need security against. Yeah. Yeah, and like.
Your k was only constant.
Yeah.
Okay,
Yeah. Okay, so that's all. Thanks again, and happy birthday, Ron. Happy birth year. Any other final questions? That's not clear. They're incomparable. There's like the computational aspect is weaker, but the single server aspect is stronger, right? So yeah.
Is there some, I don't know, it's like syntactic connection to PIR, like two-server PIR versus one-server?
I think I think so. But I forget what exactly. This kind of felt like a stretch. Like what? Because I mean, we never wrote it down, and it was a long time ago, so I kind of forget. But like, there is, I think, some way of like looking at the truth table of thinking about trying to like retrieve something about a truth table of a function, which is kind of like a PIR with an exponentially long database, except that instead of trying to retrieve a point, you're trying to like make the membership queries, I guess, or I don't know, like without.
The only difference between FHE and PIR is you don't have a database, you have actually it's a sick description of the database you're trying to.
Yeah.
There's no Impala algorithm here, right? That's the difference. Like the function X are just different. Yeah, that's a different.
If you apply this connection, you don't improve your results are like got a specific like optimized filter clearly. I mean, what happens if you apply this PIR to get regard algorithms? Is it
Yeah, I don't know. I'll have to think about it. Sorry, it's been a while since I thought about the PIR connection.
What would it take to get covert algorithm for Fourier concentrated? Like it feels like k-1 out of k.
Are you talking about getting a computationally covert?
Like I wonder if I don't have a good enough intuition for sort
I see. Yeah. Right. Right. So like, I guess you can ask like maybe if you could. Okay. So I think if you could. I suspect if you could get to like polylog of n-wise, or like you get k to be up to like polylog n, then maybe you could hide it in some other queries with noise and then make it be, yeah, something like that might like plausibly work.
Something where exhaustive search over the k-tuples is not.
Yeah. Yeah. I guess then you just need maybe it's just anything super constant. Like. Well, then with like a super polynomial running time.
Wait, you said e to the minus.
It was like 1 over. So if you have k servers, oh sorry, it probably would be.
You said that like
Maybe with constant. If your epsilon is constant, then I guess it might be still polynomial time.
Okay, right.
Yeah.
Maybe the problem of learning the randomness from the queries, it's itself a sort of a passive learning problem, right? So
There's like an inversion problem.
prove that either that is like a win-win.
Yeah, maybe.
Just to say that in the algorithm with ARI, we can only do effectively low degree verifications.
Mm-hmm.
The degree of completion is really important. And here it seems the degree, we don't care about the degree at all.
Right.
So maybe that's something nice.
Yeah. I mean, I would like to think about it more, but like I said, I shamefully just threw up a bunch of questions that I haven't thought about very much. So I guess you can scoop me if you want, or we can work together. Yeah. Instead of scooping me, I'm happy to talk about any of this with anybody. Yeah. There we go.
Yes, thank the speaker. Okay, and we have another break.
He's back at BU, and he's going to tell us about protecting cryptography against self-incrimination.
Yeah. Thanks, Daniel. Very nice to be here to celebrate Ron. Actually, I'm old enough, and so is Ron, that neither of us were at BU at the time, but it's okay. We're graying, more gray. It's okay. So. It's a nice view, right? So I'm here to talk about a topic at the intersection of cryptography and the law. There will be parts of it that are, I need to do a little bit of discussion about law stuff, but there will also be lots of crypto involved. The question at the heart of what I'm going to talk about today is a very simple question. So if you have a phone or a laptop that uses cryptography, encryption, to protect data at rest, the question that I want to talk about today is, can the police compel you to enter the passcode in order to unlock the device? Okay, so I want to be very clear about this question, right? So I'm talking about phones that are protected using passwords or passcodes, not biometrics, not Face ID, Touch ID type stuff. For biometrics, as we'll see, the answer is almost surely yes, they can. And also, the question is about whether the police can compel you to enter the code, and not a question of whether they can compel you to disclose the passcode or password to them. With the exception, I'll say a little bit about that on the next slide. But for 95% of the talk, this is the question. Okay, so I think this is a very nice question to explore for a variety of reasons. It's kind of a question at this intersection, or forms a nice bridge between these questions of crypto and computing sciences and law and public policy. And this is like a two-sided connection, a two-sided bridge. There's the most obvious direction that's like, if the answer to this question is yes, then it's an example of the law influencing what we can achieve in terms of security guarantees for the systems that we build. But this is like the most obvious connection, but there's a more subtle and in some sense more elegant one that I want to try to convince you of by the end of the talk, which is that the way that we reason and think about the world in cryptography and the language that we use as cryptographers provides us with a new lens and a new way to actually interpret the relevant law in question, and that we as cryptographers might actually have something to contribute to this specific legal question. Okay, so I'm not going to spend too much time waxing poetic about this. Hopefully this point will come through by the end of the talk. Okay, so that's where I hope to get to. But at the beginning, let me give you two things that you need to know about this question, right? So the question is, can the police compel you to enter the passcode to unlock your phone? Okay, the first thing to know is that nobody knows the answer to this question. Like, it is a giant open question. There's plenty of people who have answers to this question. There's no shortage of people who will claim the answer to this question. As Aloni puts it, like, for any possible answer to this question, there is some court case somewhere or some legal scholar somewhere that has written it for any possible answer, even the obvious really wrong ones. Okay, so what is obviously wrong, I will leave in the, as an exercise for the reader. But okay, so just to say how much diversity there is in answers to this question, I have a 2x2 table here where we can think of now, for this one slide only, I will think about both the question of, can the police compel you to enter your passcode, and also the stronger question of, can the police compel you to just give your passcode over? And it turns out that this question has appeared in many different courts, and especially active at the state court level. And there's actually 4 states whose state supreme courts have issued decisions on this. Okay, and I have a 2x2 table here. Hopefully you see where this is going. They've issued every possible outcome among this set of choices. PSA, that like here in Massachusetts, the Supreme Judicial Court has ruled that the police can compel you to unlock your device, and you do not have a recourse against this, right? You have to do it. Okay, so this is a giant open, it's both a timely question and a giant can of worms. It's an uncertain question. And there are a lot of reasons for why this is an uncertain question. One of many reasons why this is uncertain, I'll point to this quote from a much longer article that goes into much more things than I'll say today by Professor Oren Kerr, who's a law professor at Berkeley, who says basically something that, you know, as computer scientists probably isn't all too surprising to us, that like when you try to take a new technology like encryption and try to make analogies to the older things that already have precedents that the lawyers are familiar with, this is hard. And the way that you do this, the actual way that you build an analogy, will influence the answer to the question that you get. Okay? So that's the first thing to know about this question. Nobody knows the answer. The second thing to know about this question is it's actually very different than the normal question that we've heard of, at least within, you know, crypto and computer security, that we think of as like the traditional crypto wars. Right? Usually when we think of crypto wars, we think of things like government backdoors. We think of things like government searches through your devices, and like things like, you know, warrants and whatnot. I have some stickers of like screenshots of wallpapers that the EFF makes available for people to use. And the thing to know about this question is it actually sidesteps all of that. It's actually very devious and intelligent from the police point of view. I'll give them credit for that, right? So the reason that this is very sidestepping all this is that all of the questions we usually talk about with the crypto war, like backdoors and government searches, those cover in the US Constitution. I'm going to oversimplify the law a bit, but like more or less those fall under the 4th Amendment, right? This question about like your right to be safe against unreasonable searches by the police. And here, from a legal perspective, the government is not actually searching through your phone. They're just compelling you to do it, right? And so actually, this isn't primarily a 4th Amendment question at all. The main thing that it touches on is the 5th Amendment to the US Constitution. So fair warning, pretty much everything I'm going to say for today's talk is going to be centered around United States law. But some equivalents to this kind of idea exist in many different countries across the world. So the 5th Amendment does many different things, but the one part that's relevant to us today is that it states that no person shall be compelled in any criminal case to be a witness against himself. Okay, so, and this protection is very wide-ranging. Basically what it says is you have the right to stay silent so that you don't incriminate yourself, okay? And so as I said, many countries across the world have some notion of a right to silence within their constitutions or legal systems. Within the United States, though, this isn't a definitive right to silence. It's a right against self-incrimination. And that's a subtle distinction, but it turns out to be an important distinction when it comes to crypto. Okay, so I need to give a little bit of a deep dive into the Fifth Amendment case law, at least as it's relevant to this question. So indulge me for 5 minutes of case law stuff. Don't worry, I'm going to give you plenty of math equations and security reductions and all later. It'll all come later, but for now, just humor me. So okay, so the way that this comes up in a legal context is basically we can think of it as an interactive protocol between the government and somebody who's trying to be compelled. We'll call this person the respondent. Okay, so the government comes and says, please unlock this phone. And the respondent pleads the fifth, right? This thing you see on cop shows on TV, right? Which is super important to do. If you just voluntarily unlock the phone, nothing I'm going to say afterward today is going to help you. You've unlocked the phone for them. So you have to assert your right against self-incrimination. And then the police goes to a court, to a judge, and says, please compel this respondent to perform this action. Okay, so importantly, this right to silence is not some absolute right to never participate and help the government. There are certain things that you cannot refuse. An example of that, this would be something like provide a fingerprint sample, or there's a variety of different things that you cannot refuse. And in particular, this Fifth Amendment privilege only applies when actions are all three of the following: compelled, incriminating, and testimonial. Okay, so the compelled part means that this three-round protocol actually has to happen. You have to have get to the point where you get a judge to try to determine whether this is compelled or not. If you voluntarily just do something that the police asks you to do, and asks when you're talking to police, may not feel as voluntary as it will later be claimed to be in a court, but if you voluntarily just do what they say, there's nothing that you have as a recourse for saying, please suppress this evidence after the fact. You've given them the stuff, right? So perhaps the most relevant, the only thing that I will give today that even remotely approaches legal advice is I would strongly recommend that you spend 20 minutes over the weekend looking up this video called Don't Talk to the Police. It's a really good description. It's about 20 minutes long, and there's a second half that you don't have to watch, but it's an incredibly good description that goes through and describes no matter how truthful or how exculpatory or how benign you might say something to the police, there's always a chance that it might come back and become a key piece that is used against you in a criminal trial. Okay, and that's the reason that this protection exists. Okay, so for this privilege to hold, the action has to be compelled. It also has to be incriminating. This is a really, really light standard. Pretty much anything you ever say to the police has the potential to be incriminating. There's 10,000 federal laws, then anything you say might have some chance of breaking one of them. This is very easy, let's ignore it. The most interesting part is this claim that it has to be testimonial. This turns out to be the most relevant part of the law for crypto, so let's delve into it further. So testimony, yes? So it doesn't have to actually be that your answer would be something used against you. It's just that it has to have the potential to be used against you. The Supreme Court and other courts in the United States have consistently said, I should have put a quote on this slide, that the Fifth Amendment privilege is not just a privilege for the guilty. It's specifically a privilege that is also for the innocent, because statements that even innocent people might say to the police have the potential to make the police believe that they have committed a crime and could potentially be used against them. There's no admission of guilt. There's details and caveats to everything. You should talk to a lawyer, like the person behind you. But the courts are not going to be able to use the fact of you taking the fifth as prejudice, as saying this means that you are guilty. Basically, to a first approximation, the fact that this is potentially incriminating, think of it as if the court grants you immunity, then you no longer have the Fifth Amendment privilege, because it can't be incriminating to you because they've given you immunity. This is subtle because depending on what they've given you immunity to, it might also be the case that you're oh, but it might implicate me in other crimes that you haven't given me immunity for. But think of it as basically just saying, as long as you don't have immunity yet, this prong is satisfied. It's more subtle than this, but this is a very good first approximation, I think. Yeah, good question. Yeah, feel free to ask questions at any time. Great. Okay, so this testimonial part turns out to be the key piece to whether crypto can be compelled. And testimony here means basically, does it reveal something about the contents of your mind? Okay, and so testimony, as it's developed in the case law, has a few pieces. First of all, the most obvious thing that is deemed to be testimonial and therefore not compellable is if the output of the thing that they've asked you to do directly reveals the contents of your mind. The most obvious examples of this are if they force you to write something or to say something, like write down a confession to the crime. You say, no, I plead the fifth. This is an absolute defense. They cannot compel you to do such a thing. Okay? But if we only made the testimonial privilege apply to direct testimony, then it wouldn't be sufficiently robust against like side channel type leakage, we might call it as cryptographers, right? That like, suppose the police is like not, okay, don't write that you committed the crime, just raise your hand if you did commit the crime, right? You're not actually writing something down on paper, you're not actually saying something, but the act of what you're doing reveals something about the contents of your mind, and that's not allowed either. That also falls under the goal of testimony. It's called implicit testimony, and is also protected under the Fifth Amendment. But there is a loophole to this part, that if something is implicit testimony, it can still be compelled anyway if it's something what's called a foregone conclusion. Okay? And this foregone conclusion, at a very rough level, means that like whatever those testimonial aspects were, the government kind of knew them anyway. Okay? And figuring out how to formalize that is going to be the purpose of this whole talk. Okay, so to give an example, the 1976 court case Fisher versus United States that created this foregone conclusion doctrine, the question at play here was about a taxpayer who I think was accused of tax fraud of some form. And the government was basically compelling the person to go bring the documents that their accountant had produced for them. Okay, so these documents were things that already were created in the past. The government wasn't compelling their creation. They already existed. So there was no direct testimony aspect to this question. The only question was about like the only thing that was being compelled was the act of production, of providing these documents. Okay, so there wasn't a direct testimony question. There was perhaps an implicit testimony question, right? So if the government compels you go bring these documents and you go and do it, you are implicitly testifying that you know that the documents exist, that you know where they are, and you know they're the documents that they were actually asking you about, right? So you know their existence, location, and authenticity. Is basically the way the court described it, right? But in this particular example, the government actually knew all of this stuff. They had evidence, they had eyewitnesses, they had people who to say all of this information was known about this particular respondent, right? So it turned out it was the testimonial aspects of providing the documents were a foregone conclusion. This person would have been compelled to do so, right? Note that the government had no idea what was in the documents themselves. That's why they were compelling them. But that doesn't matter for the purpose of this question. What matters is how much it's revealing about the contents of your mind. Okay, does that make sense? Any questions about that? Okay, great. Yeah. In this particular example, yes. Yes, that's right. Right, so basically the government already had evidence that the defendant in this case knew where the documents were and therefore had the ability to produce them. It didn't matter whether or not the government knew the location itself. They knew that the respondent knew the location because being able to provide documents shows that you know the location as the respondent.
So even like producing the documents is maybe giving evidence about your previous state of mind, but it doesn't count as testimony because it's already written down somewhere?
Right. The documents themselves might have been, it might be your diary, it might contain your previous thoughts, but it's not the government compelling your thoughts, it's the government compelling your diary, which is a physical object that exists in the world that is not in your mind. Which interestingly relates to crypto, right? Where you might want to use something in your mind to encrypt the thoughts in the diary, which is the crux of the whole question. Yes.
So I'm a law professor, but I know nothing about criminal law. So, as this question will reveal, so companies are subpoenaed all the time.
Yeah.
And subpoenaed for documents that the government doesn't necessarily know exist.
Right.
Does that mean that officials or executives in those companies who might be subject to criminal prosecution can resist the production?
So my understanding of this doctrine is that companies themselves do not have Fifth Amendment rights. The company as an entity can't refuse any, like when they get compelled. If there's a case that potentially implicates an individual within that company, then that person in their individual capacity could totally plead the Fifth, yes.
All right, we'll have to talk about this another time, because it's really interesting because in many of these cases, it's a potential criminal action against the company and, potentially
Right.
the senior executives within the company, so it's sort of interesting. Anyway.
Right, agreed. Yevgeny, yes.
An individual say, listen, I have no idea there was any communication between you and whatever this other person. That other person uses like foreign mail service we cannot do. But if there exists, there was any prior communication between you and the person, please show all those emails.
Right.
Refusal, because you're saying those things, so if they exist, they already exist.
Right, that's a great question. So these open-ended, like show us all of the communications you might have had with somebody. Typically, those are things you can resist because if somebody can't prove how many of them happen, we'll get into a concrete example like this later. I mean, this is not hard and fast legal advice. None of what I'm saying is legal advice. I'm not a lawyer. Do not try to use any of the things I'm about to say today in court. You'll probably get laughed out, right? But we'll give an example of something sort of related to this. It's a good question. Okay. Great, so this is basically my one-slide summary of what is testimony, right? Like as Stacy said, this would be like an entire crim law class that would take many weeks, and I've boiled it down to 5 minutes, so let's not consider ourselves experts in this. But the relevant part here is this, this question about, the government knowing the testimonial aspects of the action, the parts of it that relate to the contents of your mind, and specifically like the actions you would have to take and how much that reveals about your mind as part of this act of production, okay? And so for crypto, the relevant question here is how to extend that doctrine so that it applies to, to these like acts of performance, such as typing in the password to your phone that causes it to be unlocked, right? So if we try to use just this like three-pronged thing that came from the Fisher court case from 1976 and say like, what does typing in the password reveal about whether the phone exists? Actually, okay, it reveals, that one works pretty well. It does reveal quite a lot about whether the phone exists. What does it reveal about the location of the phone? What does it reveal about the authenticity? These are weird questions with no obvious answers. And this is where like all legal analyses of how encryption, how this foregone conclusion doctrine applies to crypto gets stuck. Like figuring out what the heck that means and trying to write some 70-page law essay. Thanks, sorry, Stacy. Your field is great, but it's weird. So writing 70-page essays about like, here's what crypto reveals about the authenticity, or here's what the framers as originalists would have thought of cryptography. Like there are papers on this. I don't get it, but whatever, right? So people are lost. Yes. Yes, right. But it does actually reveal, among other things, that the phone is yours. And so, for example, if the government doesn't already know that the phone is yours, that's totally a reason you could, you say, like, you don't know that I have a phone. You don't know that a phone attached to Mayank exists. If you don't have evidence of this, you can't compel me to type in my phone to my password to this random device. Yeah, you had a question earlier? Okay, great. Okay, so basically what I'm saying is there's like a type mismatch where lawyers are going to law, and they took this precedent-setting case of Fisher versus US. They saw there was this three-prong test, and they were like, how does this three prongs, evidence, location, and authenticity, apply to crypto? Right? This is like an act of fitting a square peg into a round hole. It doesn't work. Okay, so our idea is to basically go back to that original Fisher case. It turned out that the Supreme Court was very nice back in 1976, and they gave us actually more than just this one case, like this one description of this taxpayer with their documents. They actually told us what is the foregone conclusion doctrine. Okay, so I've given you a primer on law, but now bring back your crypto hats. I'm going to read this paragraph out loud, but think of it as a cryptographer now, right? So it says, surely the government is in no way relying on the truth-telling of that taxpayer to prove the existence of or access to his documents. The existence and location of the papers, based on the evidence that they already had, are a foregone conclusion, and the taxpayer adds little or nothing to the sum total of the government's information by conceding that he, in fact, has the papers. So as cryptographers, this is a fascinating paragraph to me. It's really cool, right? Because in some sense, the Supreme Court has thought about this question in exactly the same way as cryptographers think about security definitions, right? This part at the bottom of the paragraph about how it adds little or nothing to the sum total of the government's information, this is what cryptographers call simulation. This is exactly what it is, right? This is from 1976. Not all of us existed back then. Those of us who did were not thinking about simulation back then. Yes, I know you did. Yes? Yeah, it hadn't, right? Like maybe we should credit the Supreme Court also for this, right? Okay, great. This is exactly cryptographic simulation. This is the thing that they're all trapped on, but like they didn't think about, let's analyze, the compellability of crypto from this. They thought about, let's analyze it under this existence, location, authenticity test, which doesn't go well, right? So let's go back to the source. Let's go back to the actual definition and do it. And okay, so while we're looking at this paragraph, there's actually an earlier part that proposes another possible definition, right? This idea of relying upon the truth-telling of the respondent. This is like a game-based, definition where we could say there's like a game and then there's a challenger, and like, we try to see based on the different responses of the respondent, can we distinguish the two, right? So these are two possible definitions. So one interesting thing is that both of these phrases are very connected with crypto. Another thing that's interesting is that they're different concepts, right? As cryptographers, we know that simulation-based security definitions and game-based security definitions usually do not correspond to the same thing. But in the legal community, this is something that they don't know, and this is something that they haven't realized. My pure conjecture here is that, first of all, this whole space is a giant mess. Nobody knows what they're doing. But also that people are talking past each other, because some people are writing papers that are implicitly using that top notion, and some people are writing papers that are implicitly using that bottom notion, and they're actually arguing about different standards without realizing it, right? Even worse, like most of the court cases that have existed so far about things like that taxpayer example that I gave you, if you apply either of these two standards, you get to the same answer, right? But if you apply it with crypto, you get to different answers. So maybe rather than thinking of like encryption is the thing that has like mucked up this legal question, it's actually the example that has revealed that these are different standards in the first place. Okay, great. So coming to the contributions of the two papers that I want to talk about today, the first is something that Sarah Scheffler and I wrote. I should have said this from the first slide. This is all based on joint works with Sarah Scheffler and Luowen Qian, both of whom were at BU for part of this work, but now Luowen is at Chicago and Sarah is at Princeton. Okay, so Sarah and I started by looking at that last sentence that adds little or nothing and trying to form a definition of that. And then showing how, okay, this is definition, we just make up a definition and assert that it has something to do with the law. We actually have a whole section where we show painstakingly, and by we I mean Sarah, shows painstakingly that it like agrees with a lot of the court decisions on non-crypto cases. Crypto's a mess, we don't look at those. And then also look at like the compellability of decryption and also other cryptographic things while we're at it, and talk about how to bolster the strength of cryptography against this threat. I'll get to that later. Okay, so a reminder of my caveat, none of us are lawyers, this is not legal advice. And also, like, this is something that, there's no consensus here. In fact, we don't even all agree with each other. So when Sarah and I presented this work to Luowen, he was like, that's an amazing, fascinating idea to like formalize using crypto this doctrine. But the thing is, I just disagree with you on the answer. I think that crypto is compellable and you're just reading the doctrine wrong, and the other sentence is like the right one to follow. And so we were like, okay, well, we don't know if we agree with you, but like, let's try to figure out what that definition would look like. And so we have a second paper showing what that definition looks like. So I'll try to spend most of the rest of my time showing you both of these two ideas. Okay, so before we go on forward, just want to be clear about some things that are not goals of either of these papers. We are not trying to mechanize the law and say that the law can be like computerized and run by robots and whatever. Actually, you'll see that the definitions that we have very much work within the existing legal framework and require the existence of a human judge, right? It does not get away from that at all. We also are only touching on this question of what is or is not a foregone conclusion. But if you remember, like, foregone conclusion, this only applies if something is implicit testimony. If something is direct testimony, like they just compel you to write a confession letter, it doesn't matter everything I'm going to say. That is just not allowed, whether or not it would be constituted as a foregone conclusion. So again, this is another reason why we need to work within the existing judicial system. Some human has to decide that first. Okay, and we also make no claim that like this is the correct answer to the legal question, because it's just a giant mess and nobody knows. And even if it was the correct answer, then like 9 people in robes tomorrow could write a new opinion that says that the answer is now something else, right? So in some sense, working in this field, you never know if what you're doing is right, so why do it? And I give sort of 2 answers as to why to do it. One is if we can actually write this notion of law as an actual formal definition, then it allows us not just to reason about court cases that are occurring, but about possible issues with crypto technologies that are not yet having any court cases about them, that don't have any case law. We can actually apply it, extrapolate the ideas to new primitives, and think about things beyond encryption like MPC, zero knowledge, et cetera, right? And the second thing, I think the most useful piece here, is that definitions are falsifiable, right? And so if you disagree with me as a matter of the law, you can point to the part in my definition where you disagree, right? Which is exactly what Aloni did after Sarah and I wrote the first paper, right? And so maybe we're wrong, but at least we're putting our cards on the table and not just making an argument like I think encryption should be compellable or not compellable, but giving you basically the entirety of the reasons why. Okay, great. So let me go through both of these pieces. Okay, so I'll start with the simulation-based approach, which remember is this idea of the test here at play is things are foregone and therefore are compellable if they add little or nothing to the sum total of the government's existing information. Okay? So that's the standard that we need to figure out how to formally define, right, using math and whatnot. Okay, so in order to do that, let me unpack this phrase in different pieces. So first, we have to figure out like what is the government's information? And I can think of at least 3 possible answers for what that could be. The first answer is it could just be like the actual evidence that the police have gathered and have filed with the court in support of their motion to try to compel me to unlock my phone, right? It could be all of the information that the government happens to know whether or not they filed it with the court, right? There are obligations for transparency of the prosecution filing information with the court if they're going to use it in a court case, but there's no rule that says they have to put all of their cards on the table, that they don't have to file everything that they know about the case as part of the evidence, so they might know a little bit more. There's also the set of stuff like that the government could know, whether they know it now or not, but like if they go out and go do gumshoe, door-to-door, police work and detective work and go learn more information about, go look at other places in nature, go ask other people who are not me, right? There might be a bunch of other stuff that they could learn. And so then the question is, like, I'm just going to take the largest of these rules, like this. I'm going to say the government's information, because I want to argue actually, foreshadowing, I'm going to try to argue that decryption is not compellable. So since I'm going to argue the no case, I'll give the police the nicest berth and say the government's information is not just everything they currently know, but everything they possibly could know if they went out and did anything other than talking to me, right? And to say that it adds little or nothing to it, we have to think about like making sure that the knowledge is contained within this bigger set of potential information. The one thing that is not allowed as part of this add little or nothing is if they learn something about like this larger gray set will be the total set of all information in the universe, potentially that involves my mind, right? So the government is allowed to know anything they can in the world that doesn't involve me, but if they learn something on top of that, then it necessarily involves me. Okay, so this is using the idea of cryptographic simulation, right? This is going to be their way of sort of distinguishing between the stuff that they could have learned without me versus the stuff that they necessarily needed me in order to learn. Okay, great. So, so just to turn that into a definition, right? So here's the idea of a definition. I'm going to emphasize up front that A, this is kind of weird and wonky, and this may not actually be the truth, but B, that it does happen to align with prominent non-encryption related court cases at the US Supreme Court and circuit court levels. Okay, so we think it's a valid, reasonable attempt to capture the relevant law. So the definition is basically a thought experiment, a mental experiment, right? It says basically, you should take on the role, pretend that you are a judge who is deciding a case, and we're going to imagine what might happen if you allow this compelled action to go forward and if you don't. Okay? So first, let's think about what happens if you do allow this compelled action to happen. So there's the government in this blue person, together with this folder of evidence that they have, that they suppose you allow them to do this. So they will interact with the respondent and do the compelled action. It might be an interactive protocol, after which they also might be able to interact with everything else in the world other than the respondent. I'm just going to collectively call this nature and represent this, just because we're computer scientists, as like, a Turing machine tape of just like all the other data in the world that is not the contents of the respondent's mind. So they can interact with the respondent, they can look at stuff in nature, and eventually they return something to the judge. Okay, and at the moment, like this information, it might critically depend on the respondent's mind, it might not. At the moment, we can't say. It's just that the government has learned something through this interaction. It's something in the total set of all knowledge in the world. And then now let's take the opposite view of what happens if you deny, as the judge, this request, and therefore the government doesn't get to talk to the respondent, right? So in this alternative world, we can imagine, I'll call this SimGov, this simulator, that it gets to talk with nature and look at anything else in the world, but it doesn't get to interact with the respondent now, okay? And it can look anywhere in nature it wants. It's polytime bounded, but great. And in particular, this simulator is not constrained by the other laws of nature and laws of law, right? Like it can look at things in nature that are not within their jurisdictional boundaries. It's not constrained by what it can or cannot get a search warrant for. Like, I don't care about any of those other laws. It's just like it can look wherever it wants. It just can't talk to the respondent. Okay, and so the only constraint here is, it can't talk to the respondent. So as a result, we know that the information there has to be contained within that smaller set I defined of all the potential information in the world that doesn't, that can be found without me, right? And so the magic of simulation-based security is if we can build a simulator such that the judge could not tell the difference between these two, then it allows us to prove this negative, that the that the government has not learned, more information above and beyond what it already had the ability to do without me.
So in the
Yes.
future case, the SimGov has access to the documents.
Right, because they exist and they know, they knew somewhere like bounds on the location of where they were, and in this world, this nature is not, there's no locked doors, there's no warrant requirements, there's no whatever, they can just go fetch the papers themselves. That's right. Now, whether a real police has the ability to do this, whether they have the key to open the lock, or whether they have the search warrant to do it, turns out to be inconsequential. Once you have this capability, then our definition says you can then now go compel the respondent to do it for you.
Maybe two quick clarifications. So one thing is computational efficiency of the simulator compared to government, because maybe in this text document, presumably the government would rather than ask the judge to write these complicated responses, if they could actually search it, they would be able to do it. And maybe, sure, if they go to every hole in the world, they would find it,
Yeah.
but it might require exponential time.
That's right. So the computational efficiency does matter here for the reason you just said, yeah. And you should think of nature as an exponential tape that everyone has Oracle access to.
So in this case, I'm not sure that Fisher case would fall into this or not, right?
Yeah. In this case, they had some understanding of where it might be located.
But the other thing, does the judge have access to the tape, or the judge access to,
Yes. Everybody has access to the tape. Actually, I think, yeah. Definitely all of the other entities have access to the tape. I don't remember the judge. I think the judge has it too. Yeah, pretty sure it does.
I don't understand. So, when you give the diaries to the government,
Yeah.
you certainly have more information than without the.
Right, but that was information that you wrote down voluntarily. The government never compelled you to do it, remember? You only get protection to the actions that are compelled and incriminating and testimonial. So if the government compelled you to write the diary, that totally would be compelled testimony and would be not allowed. But the fact that you voluntarily wrote the diary, when they ask you to just go fetch it, that just revealed the only use of your mind is the fetching part. Right. Unfortunately, that doesn't matter. Yeah, that's the way the law works here, that you can still be compelled to turn that over. Yeah. It's an interesting standard. Yes?
So isn't that for every government there is a simulator?
Yeah, for the government, like basically, no, not for every government. Like for oh yeah, sorry, yes, that basically that whatever the government would do interacting with you, after interacting with you and looking at whatever in nature, there exists a simulator who could learn the same thing. Yeah, it's a standard, it's almost a standard simulation-based definition, except this weird nature thing is stuck in there, right, with this, this RAM machine with oracle access to nature. That part's weird. I also haven't told you how nature is built. So basically the way that nature works is that the respondent gets to build nature any way that it wants, as long as it's consistent with the evidence that the government has filed with the court. Okay, so if the government knows that, to Ron's question from earlier, if the government knows that the taxpayer's documents are in their safe at their house, then like nature has to put the documents in the safe at their house, right? Like but basically the point here is that the respondent gets to equivocate on anything that the government hasn't declared that they already know. Okay, and if for all possible equivocations, if it's not the case that that for all governments and all natures there exists a simulator, then this is not compellable, according to our definition. Yes. Yeah.
Against it, right? But now you're telling about nature to the smallest set that the government.
Nature is tied to the stuff that is already filed, but then the simulator can go learn anything it wants by doing detective work by looking at that nature. Yeah. Right. So one of the reasons that the nature is tied to just the evidence filed is, in some sense, we want to incentivize the dissemination of the evidence that it knows. We don't want it to be the case that our definition incentivizes hiding evidence, right? And there's many reasons for this, but that's one of the reasons why, like, basically the respondent, maybe to give an example, like, suppose the government tells you, like, hey, Kenan, please type in as the password to your phone your dog's name and your maiden's mother name and your birth year. And you're like, oh crap, that actually is my password, right? But the government didn't know that. It was just a shot in the dark, and they compelled you to do a thing, and it turns out it would work, but that doesn't matter. So you get to equivocate and say, but in the potential worlds where that wasn't my password, then then this wouldn't work, and therefore it's not compellable. Got it. Cool. Okay, great. So this is the definition, right? Just writing it out, right? That the respondent adds little or nothing to the government's information if there exists a simulator such that for all of these possible choices of nature that are consistent with the evidence that the government has filed, no judge can distinguish. There's a lot of alternations in there. I know it's kind of confusing. Let me give you another example, coming back to what Evgeny was asking about a while ago. So here's a court case I'll describe for you called US v. Bright from 2010. It concerned the Bright family, who were also tax evaders, and the IRS basically came to them, and the IRS happened to know that this family had 2 offshore bank accounts. They knew the specific banks, they knew the accounts, right, the account numbers, they knew all about them, and they said, we compel you to provide to us the bank statements for those 2 accounts plus any other offshore bank accounts you happen to have. Okay? And the court basically said, you government can compel those bank statements for the 2 accounts you know about, but you can't compel it for any other bank accounts that may exist, right? The idea here is basically like, it doesn't matter that the government doesn't have jurisdiction on these offshore accounts. That's why they needed the respondent's help in the first place, right? Because they couldn't actually just go serve a warrant to the offshore bank. The offshore bank wouldn't recognize an American warrant, and the American police couldn't go there anyway. And so, but the fact that like this SimGov could go fetch those things from those known locations meant that the government was allowed to compel those. But any other bank accounts you might have 0, you might have 10, you might have 1,000. They might be in country X, they might be in country Y. Like none of this was known to the government ahead of time, and therefore the simulator would have no way of fetching that consistently and reliably, and so that's not permissible. Yes. Well, so that's a great question. Okay, good. So if they did the first compelled act, right, just getting the 2 compelled things, and that gave them new evidence that they could then go back and make another request, they could totally do that. So we do prove in this paper, I mean, it's a simulation-based definition, and we're talking about RONFEST today, so composition is basically the question you're getting at. And this is a great question. And we prove in the paper that our definition is composable in the sense that if you make 2 requests back to back without looking at the results of the first thing for the moment, that like it basically the act of having performed the first act can't help you to do the second act. But the data that you get back from the first act, like the bank statements or the diary or something, could totally give the government more information. And even more, after that, they could then go do more detective investigative work, gather even more evidence, and come back later with the warrant, or sorry, with the subpoena for something else. And yeah, this could be possible. Yes?
Maybe the question was a little quantified, but you're saying in the real world, the government, simulated or not, doesn't have access to those offshore accounts. So how can the respondent say, okay, so I'm creating nature where these 2 things, I don't know how you model the fact that the government cannot have access to it, and because in the real world, they couldn't have done it. So
Right. In our definition, the government is not constrained by those other physical and jurisdictional boundaries. So if the government has evidence that I have a bank account with First Cayman's Bank, then they have my statements too. Whether or not I have them, but wherever I have them, the simulator could go fetch them from the bank, right?
So this seems to for all white boxes consistent with the evidence.
Yeah.
So in this case, some computational would say you have to have a well with those bank's accounts and cannot block access to simulated government.
Right. Right. Like I have an account at, let's say, First Cayman's Bank. So somewhere in the records of the computer of First Cayman's Bank, they will have my records, right? Because the government knows it exists. So like so SimGov could just point to they don't have to go to the same records. They don't have to go to my house to get the records. They could go to the bank.
But somehow the fact that those nature has to store everything in the plain text form is
Yeah.
can they like say, okay, I'm going to apply to skate it or
Yeah. This is true. We have like a generic hand waving of this question in the paper. I don't have a good answer to you. It's a good question. We basically are trying to say like this is a thought experiment, but imagine like is there some reasonable way that the SimGov could do its job? Yes or no? Yes. Yeah, basically yes. That's right. More or less. I mean, so we don't explicitly say what is the standard for like indistinguishability. Is it like perfect? Is it up to negligible error, et cetera? This is something that courts never really specify themselves, but what does it mean for the evidence to be foolproof? Evidence is almost rarely foolproof, but it's usually convincing enough if the court accepts it. And whatever that standard should be, it should also hold here. We don't specify, this is again another thing we throw to the judge. Yeah, good question. Okay, so applying this to crypto, right? So if I have an encrypted email or something somewhere in nature, and the government comes and tries to compel me to decrypt that email, right? We know from the semantic security of that email that like a simulator who just has access to the ciphertext but does not get to talk to me and therefore does not get to learn the passcode in my head has no way of figuring out this result, right? So using the simulation-based notion, the answer to this question is basically no, the government cannot compel unless there's some other way based on something else in nature that allows the government to also get this ability to decrypt, right? So for example, if I wrote my key down on paper somewhere in a place where the government knows it, or I use a hardware token, or any of 1,000 other things, I'll say more on the next slide, if there's some alternative way for accessing this content, then according to our definition, it does become compellable.
Why do you think it's reasonable to, or not reasonable to say the simulator can be inefficient? Like, I assume with all the prior court cases, they would, the deal with crypto would be consistent with an inefficient.
That's a good question. So it's actually not because of the location piece, because we say that the nature is exponential size, but if like it does matter in some of the cases that like the government knows something about the particularities of how to find the thing that you're looking for. And if that location is totally anywhere, then like a simulator that could look under every single rock would be different than a simulator who couldn't. So that's our, it's not a great explanation, but that's the best we have. Yes?
So I just want to clarify, so like the kind of the distinction here between encryption and just like a really secure lockbox
Yeah.
is like
Is the fact of it being in your mind.
well, like, but say if it's like a really secure lockbox that like it's a keypad entry,
Yeah.
so I have the key code in my mind.
Yeah.
But like a simulated government can still open that lockbox, right?
Yeah. Well, it depends. It depends on if the lockbox is penetrable, basically. Actually, no, it doesn't. Yeah, you're right. You're right.
So, I mean, it's just more like the fact that
You're right.
you're really modeling encryption as like there's no information of this actually in the world.
That's right.
Right? Like,
That's
it's
right.
Like as if that box is empty.
I agree.
If you don't have the key.
I agree. Yeah. In a sense, like your mind is the thing that is turning it into useful text, and they can't compel you to do the active performance of turning it into useful text, as opposed to opening the door, which is a different thing. Yeah.
Do you have to have like some sort of notion of verifiability of the user, right? You mentioned the semantic security of the
Oh, that's a great question. I'll come back to that in a few minutes. Yes.
Oh, what if the iPhone or something that the government could have use some very high-end physical devices to maybe detect the secret key that's stored inside? Like,
Yeah.
would that be?
If the device is vulnerable in such a way that the secret key is extractable from the device, then that's one of my constraints for the unless. So let me go to the next slide, which has basically this point, that there's a lot of times where we create crypto systems that do have the keys stored in other places in the world, usually also for like good, information security promoting reasons, okay? I mean, I have backdoors, which is not an information security promoting reason, but other than that part of the list, right? Everything else, like, there are pushes, including by Apple, Google, and Microsoft just this past week announcing a new standard for passwordless login, right? Which would mean your login is based on entirely things that you have, like tokens, or things that you are, like biometrics, none of which is protected under this testimonial privilege, right? The only factor that's protected is the contents of your mind. Additionally, right, if you enable like cloud backups, or you use a system where the manufacturer has an alternative key so that they can help you with customer service to get you back into an account if you lose access, the existence of those alternative ways that are not purely dependent upon the contents of your mind, in our opinion, change the answer to this question, okay? Even for our opinion where the answer is no. There's plenty of people who argue that all encryption is compellable. I'll get to that in a minute. Yeah, that one, almost surely, there's a few people who argue that you have a Fifth Amendment right to against, but Aloni and Sarah and I think this is wrong. That has nothing to do with the contents of your mind, right? You could be asleep, and they can unlock your device. That means it's not really depending on the contents of your mind at all. It's something you don't have this privilege to, actually, in my opinion. Unfortunately, in Massachusetts, they've ruled that even what I'm just saying is wrong, and all of it is screwed. Yes?
It's like biometrics coupled with like a stress sensor that looks at how stressed out you are while you're entering the password.
I mean, you're welcome to make such a thing. I don't know. They can't, well, whether it works or not is a different story. I'm saying they can compel it, whether or not it works.
Wouldn't the usage of that like circumstantially reveal like the contents of your mind, like why you're being able to, why?
Yeah, I don't know. So this is a fair question. I'll say more about it. Like basically, like, you could say things like, oh, but it reveals that, you speak English, or it reveals, like, there's a lot of things that it indirectly reveals about you, the fact that you're responding to this. But I don't know, I think there's a sort of common sense principle at play here in the court system. And if it turns out that their reason for asking the encryption question was really just to figure out whether you would get tense and nervous about it and use that as the evidence against you, that probably would then be disallowed. Yeah. Let me skip ahead quickly and just say, so another thing we do in this paper is talk about like, okay, so rather than, so far I've talked about when actions are compellable, right, based on the evidence the government has gathered so far. But you can turn this question on its head and say, what about the things that you and I do voluntarily in the normal course of our everyday lives? How does that increase or not increase our susceptibility to this threat? Because we're maybe creating new things that the government is fetching as evidence, okay? So we give an example of like secure multi-party computation where, all the servers, say I do outsourced MPC, all the servers that I'm collaborating with, it might be the case that the government comes and corrupts all of them because this is just a right against self-incrimination. It doesn't protect me against other people. And all those opinions were within nature. And so we designed a new garbled circuit-based MPC protocol that basically does a little bit of pre and post processing at the very beginning and end using a password-based key derivation function to derive those wire labels so that like even if all of the servers are corrupted, then it doesn't, it needs the contents of my mind to turn those wire labels back into something meaningful. So the punchline here is not whether this one, garbled circuit trick is useful or not, but that we as a crypto community should be thinking about how we design crypto systems to be, more resilient against this specific threat. So we define this notion of resilience to this foregone conclusion, FC resilience, based on sort of, we should design protocols that do not expose people to new compelled risks of threats of compelled disclosure, no matter what evidence the government had already. Okay, so I had a whole other section on verification-based approach with Aloni, but I'm running out of time, so I'm going to more or less skip this. This was about the idea of a different definition that is based on this relying on the truth-telling standard. So there's a paper where we write about that, but let me just skip in the interest of time to the conclusion, which, so I began with this question of, can the police, compel you to enter your password to unlock your phone, okay? I've been talking for an hour. Unfortunately, the answer is still, I have no idea what the answer is. Nobody has any idea. Hopefully, I've at least scared you a little bit into thinking about this question, even if we don't know the answer. And so what we've done is proposed two formal definitions of two prevailing common interpretations of the law. Sorry, I didn't say the second one. The punchline of the second one is that it does mostly allow for compelled decryption. But we also evaluate both definitions under other standards, like other crypto primitives, like what is the compellability of zero-knowledge proofs and so on. So anyway, so you can look at the papers for more details. Hopefully I've convinced you that there's these interesting connection points between crypto and the law in both directions. Maybe you're now thinking that the crypto influencing the law thing, I'll call it bad news, right? That like the fact of the existence of this legal adversary who has this power of compelling things, it doesn't cleanly follow into the security models that we make, right, as crypto and information security people more generally. It's kind of incomparable to a lot of the adversarial notions that we make, right? Where we usually will do something like in MPC, say like there's a non-collusion assumption, but then if the government can go and just compel everybody in the set, our non-collusion assumption is violated. But on the other hand, in crypto, we tend to say like the adversary is all powerful and can do all things. But here, this adversary is constrained. It is not all powerful. It does have to obey the laws that I have tried to describe today. So it's kind of incomparable to the notions that we think of, and it's something we should think of as a new kind of threat actor to add to our security definitions. And also, this good news is that we can use this machinery of crypto, simulation-based security, game-based definitions to reason about and formalize these ideas from this Fisher versus United States court case. So just my final takeaways are, for all of us as a crypto community, when thinking about the design of crypto protocols, right, we should remember that there exists this other adversary, I'll call this gov adversary, that might compel people out there in the world to use the protocols that you're designing. So when you're designing these protocols, think about the fact that they might be things that people use not of their own volition. Remember that the information that comes out of your protocol when people are voluntarily using it might be used to build evidence for a case against them to compel them to do potentially something else. And try to design protocols that are as resilient in both of these ways as possible. And remember that the power of this gov adversary is not absolute. They have to adhere to the laws. And finally, as a matter of law and public policy, to the extent that people are interested in sort of questions of public advocacy and all, this is a domain I might call it like a new front in the crypto wars. It's been ongoing since sort of the push for encryption of data at rest has been a thing for almost a decade now. So this is a matter that deserves our public attention and scrutiny and advocacy as a community, as a security community, just as much as the usual Fourth Amendment government search backdoor type stuff works. There's this weird pernicious thing that the existence of a backdoor coupled with the fact of this Fifth Amendment thing means that if a backdoor exists, then there's a way that the simulated government could learn the information, which actually makes the crypto more susceptible to being compelled, because now that there exists a way for the simulator to do it, they can now go compel you to do it. That maybe the existence of the crypto backdoor makes it easier to compel, even if they never end up using the backdoor. Like, this is a weird connection between these. And also, because we as a crypto community, we're both impacted by this question, but also I think we as a community have an interesting perspective by thinking about how to explain to lawyers and to the legal community these questions of simulation and all, and how they influence this foregone conclusion doctrine. So I'd like to issue a call to arms for us to be thinking about, and as these cases progress, and there's people who look at this think that the US Supreme Court is very likely to take a case of this in the next couple of years, that we as a crypto community should be thinking about what we can do to provide amicus briefs, whatever, things in support of this. Okay, sorry to go over time. Thanks, everyone. Yeah.
In the real world, intuitively, it seems like whether or not, let's say, government knows they have some evidence so I could access it, but without me, I mean, in theory, they could access this Cayman Islands account, but in practice, everybody knows they cannot. To me, it means that there is no way they can compel me, right? So somehow, to me, it seems like there has to be the quantifiable nature. Either it has to be the real nature, or the nature that everybody knows exists, or it has to be within, the confines of reasonable nature.
Yeah.
Or there has to be an explicit thing saying, listen, the simulator is at most quadratically slower than the thing is saving taxpayers' money kind of.
Yeah. So we have a 2-page discussion section on pretty much all of these points, which is great. Definitely take a look. It might be more than 2 pages. It's the overhead of the simulator definitely matters. This is why, one of the reasons why we have the respondent be in charge of creating the nature questions, subject to the fact that it's consistent with the government's evidence. And maybe the government's evidence includes the fact that they know that that bank that you had described earlier, has records unobfuscated, that they have their records in a known way, right? Whatever the government knows about the world, the respondent has to obey that, but otherwise we give it full equivocation to sort of punt on that to be as hard on the government as possible.
Should the government be asked to not accept the single purchase exist, actually to put it in?
Yeah, we think it should be a constructivist definition, yeah. That in a sense, when like I told you at the beginning, what happens in practice is the government compels you to do something. You should assert your Fifth Amendment rights. If you learn nothing else from this talk, please go watch that video. It's great. And then they go to a court to compel it. And our view is when they go to the court to compel it, they should describe the simulator.
So there was a question about verification, which I think is also very important here.
Yeah.
So let's say I one time had the secret
Yeah.
that I'm being compelled to reveal or something. I could choose to give any key. The
Yeah.
key's in my mind. Even
Good.
under, even if we take Massachusetts view where, they can still
Yeah.
compel me with the key in my mind. They wouldn't know if I gave them their key or not.
Right. This is a good question. Sorry, I skipped the slides relevant to the question from earlier. Actually, there have been court cases on deniable encryption, which is really cool. It came up in a few court cases where people were using a software package called TrueCrypt. And but this question of whether the use of so most encryption for say your phones are actually committing encryption or something reasonably close thereof, which causes problems. There are a good number of people who even among those, okay, so let me say this. Our second definition basically says that encryption is generally compellable, but if it's deniable, then it's not, for the reason that you said, that you can be compelled, but you can provide the duress password instead. You can provide any of them that you want. Unfortunately, in Massachusetts, the Supreme Judicial Court, basically, the case there did involve TrueCrypt, and they said, we just compel you to enter the right password and not the duress one, which in my opinion is the epitome of relying on the truth-telling of the person to do it.
It's unclear if the judge even can know if you inserted the right password.
That's why I think it's relying on the truth-telling.
Okay,
Yeah. Yeah, so basically our second definition, which I skipped over, sorry, is basically the government can compel anything that they know how they would verify it later. And the action of compelling is just do anything that causes this to verify. And so if their compelled action is unlock this phone that uses deniable encryption, you can do whatever you want to make it revealed. Yes?
So going back to sort of Oren Kerr's point about analogies, the courts that have ruled that you can be required to provide your password, have they relied on a key analogy? Like if you have a physical key, then you can be compelled to open it, and that's not revealing the contents of your mind. And where I'm going with this is that the law evolves in response to normative concerns, not
Yeah.
formalistic
Yeah.
ones. And so I wonder whether if courts are persuaded by that sort of the spirit of that analogy,
Yeah.
the Supreme Court might just change the formalist statement of the law
Yeah.
to achieve those goals.
Yeah, so the two parts. So the first part, I don't think it's the key itself that they're really making the analogy to, so much as the earlier question was about a safe. This is sort of the usual way that they think of it, is like there's some documents that are behind a safe. And so whatever is used, whether it's called a key or not, is not really the relevant piece. It could be a number lock, it could be in anything. But in like normal safes, the belief is like, okay, if the question is about the active production of the documents inside of the safe, well, as long as they know that you have the ability to get into the safe, then that's what happens. And the question is sort of, does encryption or decryption use your mind in a more substantial way? And the way that like Sarah and I wrote our first paper, we believe the answer is yes, that like, in a sense, encryption is, or like decryption is basically like it's like converting the documents from one language to another, from this language of ciphertext land to this language of plaintext land, using the contents of your mind to do so. That it's something above and beyond just like a treasure locked behind a door, which is the usual way that the courts are thinking of this. Sorry?
It's a non-black box use of the document.
That's right. That's what we're trying to argue, basically. And that's like the linchpin of, if you don't believe us on that, then that's where the disagreement lies. To the normative piece, I fully agree. I had a comment on this, but I forgot it. So anyway, I'll find you later.
Has anybody tried like the Holmgren interview definition? I don't know if it makes sense, but like intuitively, for the Cayman Islands example, it would be something like, the judge can't just compel me to open it. Can always say no, but then the judge can say, okay, I'm giving government the authority to go and retrieve those records by other means, like pretending to be a simulator. If they fail, you're not liable. I cannot punish you for not doing voluntarily.
Yeah.
But maybe if they succeed, you have to pay the cost of like military invasion in the Cayman Islands. The government will want to do it, but roughly speaking, the extra cost the government has to do it, but it has to be conditional on the success. If the government actually fails or decides not to invade Cayman Islands, I'm not liable. I don't know. Is it something meaningful? Or?
I don't know. Yeah, I mean, the goal here is to try to provide, like, this Fifth Amendment right against self-incrimination, when it does apply, it is an absolute right. There is no alternative recourse against it. The question is just whether it applies or not. And the goal is to try to come up with some way of formalizing, whether it does apply. But if there's uncertainty about whether it applies, the burden of proof is on the government to show that they do have the right to compel you. So my point is, any uncertainty, if the court believes genuinely that there's uncertainty, it would be decided, I would think, in the favor of the respondent, because the burden is on the government. They're the ones who went to the court. They're the ones who are filing this motion. The burden is on them to prove that they have the right to force you to do this.
I guess in the sort of concrete example that is a fairly close analogy to the safes is like if I have a password manager where I
Yeah.
explicitly know the password to whatever my service is, if I know the password to get to the password.
Right.
Does that fall under any like existing scenarios that you've considered?
I don't think the fact of a password manager, I don't think super changes this question in the sense that it's just one level of indirection, but it's the same question. Whether you believe the decryption should be compellable or not would probably be the same as whether you believe that the entry of the password into the password manager to unlock it for the police to then use it to then get access to whatever thing. I don't think it would fundamentally change that. I don't know. But I do think that there's something, this is maybe Sarah and I waxing poetic about, back in the day when we walked uphill in the snow. But like, I think there's something interesting about passwords specifically, at least as it pertains to this question of testimony, relative to other forms of authentication that we would like to see stick around. And maybe not even stick around in the form of like, right now we have to create whatever 16-character totally random passwords against, hackers across the world. And maybe if you can design a non-password based mechanism to defeat that, then we just need passwords that are strong enough to defeat, the local police department, right? Which may be a different strength of security of passwords that we need, even if we still leave them around for this purpose. That's sort of my opinion. Yes.
So if I'm using, for example, Google's password manager, and it seems like the government can compel Google to review my password, right?
I don't know how, it depends on how these password managers work. Are you saying one with like a cloud backup where they know your?
Like without me, the government can query Google, which is part of nature, to access my password.
Yeah, that's my belief, yeah. Remember, if the passwords are actually physically stored with Google, they also can do the Fourth Amendment thing of go and get a warrant and just get it from Google. That's also a possibility, in addition to everything I'm talking about here, which is whether they can compel you to do it. And remember, I'm just telling you my theory on whether they can compel you to do it. Every single court has come up with every possible interpretation of all of this. There are courts that have said that biometrics are even falling under this. There are courts that say deniable encryption doesn't fall under this. Like, there's a whole spectrum, and I don't understand a lot of the decisions made, so I've just given you my perspective. But yeah, remember that the existing search stuff, even though I discounted it at the beginning, that very much is also a government power that exists.